Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Okay, step on inside, and if you are continuing this video series for Integrated Math 2 in the Big Ideas Math textbook, we are now on section 3.3, graphing f of x equals ax squared plus bx plus c. I'm looking at the camera, but I think in the corner of my eye somebody homered. It looks like he's trotting, rounding third, and heading home. So Diamondbacks, congratulations to what you're doing. Anyway, so this is also known as standard form. Ax squared plus bx plus c. Check it out in the title. And in fact, while you're here, check out the description section down below where you are going to see a PDF upload of this textbook section, some graph paper that we are going to be using, timestamps to each individual problem or the sections of the problems, and this continued playlist. If you're in the wrong section of this playlist, go ahead and click on that playlist, find 3.1, 3.2, find the quiz review, whatever it is that I'm going to have uploaded at the time that you access this. Anyway, this is also known as standard form. So far we've used, not vertex form yet. I'm going to get to vertex form with you guys in a bit, but we've used ax squared and then ax squared plus c, and this is more of the whole enchilada. This is an actual form now, standard form. And out of standard form, we now have to find our vertex in a very specific way. And we're going to see that in the book. I assume that the book does it the way that anyone else does this here. It's going to be kind of wicked looking, but once you kind of grasp it, it'll make a little more sense. I'm kind of a little backwards on things in that I would have preferred doing chapter 4 first because I can explain the reason why things exist here based on what we do in chapter 4. But that's okay. At some point, I'll go back and say, you see, that's why we did this in chapter 3 at the time when we're actually in chapter 4. Anyway, without further ado, guys, let's go ahead and move forward and see what it is that we have. And I'm serious. I have no idea what it is that we have either. I love sight reading this with you guys. All right, what we will learn. We'll learn to graph quadratic functions in the form f of x equals ax squared plus bx plus c, also known as standard form. And I don't know if they're going to say that, so I'm going to go ahead and say that right now. Also known as standard form. And what's interesting is, as we know standard form, as we're aware of it, standard form is descending order of degree. Degree 2, degree 1, degree 0. And they're probably going to say this. Note that A is the only one that cannot be 0. These are allowed to be 0 at any time. We've seen it so far with B and C as 0, and we've seen it with B as 0. And now we're going to have some sort of B value. So we'll see how this affects things. Graphing f of x, and we're going to find maximum and minimum values of quadratic functions. It doesn't say anything about real life applications. They almost always say that. Now, I'm guessing with the maximum and minimum things that we are going to be doing real life applications. That's part of it. Find the maximum profit of this and that. So that probably has to do with it. Okay, max and min value are two brand new terms. So we'll go ahead and refer to those in a bit. Okay, graphing f of x equals ax squared plus bx plus c. And yep, they are doing it. Let's see what's going on. This core concept. The graph opens up when a is greater than 0 and opens down when a is less than 0. We've done that. Now check this one out. The y-intercept is c. Now in the last section, c was more or less a vertical translation. It only went up and down, and that's what we talked about with regard to the vertex. And the vertex was the same as the y-intercept. It always seemed to be. But now, as you can tell, we're going to see vertexes that are not on the y-axis itself. They are not necessarily the y-intercept. So don't assume that crossing the y-axis always means you're just going to bounce right off that. No. Now your vertex can be elsewhere. Your axis of symmetry can be elsewhere. But there is still a y-intercept, and it is still at c, because when x is 0, y is c. Seems to make sense. And the x-coordinate of the vertex is negative b over 2a. Okay, here is the new part right here. And I know it looks really strange, this negative b over 2a. And as I stated, I can't really state what this is all about right now until chapter 4. I could. I'm sure the book has some version of talking about it. But it makes it a lot more clear. It makes a lot more sense if you see this later in chapter 4 with regard to why this is. But go with it for now. Negative b over 2a. Take the opposite. And b is your linear coefficient, and a is your quadratic coefficient. Not with the x's, just the numbers themselves, even if they're 0 or 1 or whatever. Okay, and then so there's kind of a complete picture of a right side up facing graph where a is greater than 0. We have a vertex. The x value is at negative b over 2a. You have also a y-intercept at 0, c. And as long as we use what I used in the previous sections for doing stretch factors with A and applying this 1, 1, 2, 4, 3, 9 thing and multiplying by things, then I'll still be going without a table, and I can confirm that the point that we hit is 0, C, as I always anticipated with our graphs. So just be on high alert there. What else do I want to say about this? And then just the axis of symmetry. They also say the axis of symmetry is at x equals negative b over 2a. Remember, if the x coordinate of the vertex is there and your axis of symmetry line goes through there, they'll be the same thing. You don't have to think of one as one and one as the other. Just know the axis of symmetry goes through your vertex. Okay, so now they didn't mention the y value of the vertex, but hey guys, how do you find any point on any graph? You substitute the x value into your equation. So there's going to be more, I'm sure, mentioned on that once we start finding the vertexes themselves. So, well, it's right here. Finding the axis of symmetry and the vertex. So here's an example. We have y equals 2x squared plus 8x minus 1. And they want us to go ahead and find, they say the axis of symmetry first. That's fine. Let's find the axis of symmetry when a is 2 and b is 8. So here's a at 2 and b at 8. The x value of the vertex is negative b over 2a. That's also where you'll find the axis of symmetry at x equals negative b over 2a. For negative b over 2a, b is 8. We're going to take the opposite of 8. I tend to write it on top. So negative 8 over 2a, 2 times 2. Negative 8 divided by 4 is negative 2. So the axis of symmetry is the equation of the line x equals negative 2. It's a vertical line going down, x equals negative 2. That also means that's the x value of the vertex, and they ask you to find that next. Use the coordinate. So here's what they say. Use the function to find the y coordinate of the vertex. For f of x equals 2x squared plus 8x plus 1, we're going to do f of negative 2 equals 2 times negative 2 squared plus 8 times negative 2. Excuse me, I said plus 1, minus 1. Minus 1. Now they say equals negative 9 straight up. Use order of operations. But let me break this down a little bit more. Negative 2 squared is 4. Remember, you do that first. And 2 times 4 is 8. And then you have 8 times negative 2, which is negative 16. And then that minus 1. So 8 minus 16 is negative 8. Minus 1 is indeed negative 9. And there's more I'm going to say about these calculations later, especially if they are big or they seem like fractions and a little troublesome. What's going to help you? So the vertex is negative 2, negative 9. You substitute negative 2 for x, you get negative 9 out. It also, which they'll talk about later, it also happens to be the minimum value of your graph, right? It's a right side up facing graph, and the vertex is the bottommost point. So they have some examples down here, but of course I'm going to be doing a whole problem set, and I hope that they ask me the same kinds of questions. Oh, they show you the graph right here on a graphing calculator. So there's the vertex. Here's the axis of symmetry, x equals negative 2. Okay, let's go ahead and on this one, let's describe the domain and range with this set right here. Now, the domain, I'm going to say straight up for you guys, wherever it is all real numbers. Oh, I'm sorry, they ask us to graph this. We're going to go straight up. Graph this, describe the domain and range. Now, in order to graph this, what you want to do is find the vertex. Before, the vertex was significantly easier. Hold on a second, guys. I'm actually getting a phone call. I hear a vibration. 1 second. Okay, I am back, and I don't remember where. I don't think I really started the problem, so let me just say it again. We're going to graph f of x equals 3x squared minus 6x plus 5 and describe the domain and range. So in order to graph this one, we do want to find the vertex. Before, the vertex was pretty easily found, before it was on the origin or on 0, c. Now we have to use that negative b over 2a concept to find the x value of the vertex. And I say have to in the way that this is the only method that we know at this point, and there's no other way that we know how to get to another method. So out of standard form, your goal, and this is whether or not you want to use a table, because even if you want to use a table, you still want to find the vertex x value, because you want to build your table around the x value. And I imagine, because I don't know where they do their graph things yet, I got to find out, or like how they find their points, but I imagine that they probably use a table to find all the remaining points. You want to build it around your vertex. So how do they find the x value of their vertex? Negative b over 2a. Now, negative b is the opposite of negative 6, which is 6. Over 2a, a is 3, 2 times 3 is 6. So 6 over 6 is 1. That's where they get that. Now, to find the y value of the vertex, they substitute 1 for x into this equation. So here, they have 3 times 1 squared minus 6 times 1 plus 5. 1 squared is 1 times 3 is 3, minus 6 is negative 3, plus 5 is 2. So they have the point 1, 2 as their vertex, and you can see that on this portion of this graph here. Let's say that this is all that was built so far. Now, the y-intercept is also a value. You know, there's a reason why they mentioned the y-intercept, despite the fact that standard form has it, is that it gets you 2 additional points. 2 of them. The y-intercept is one of them. And then we can reflect that across the axis of symmetry. Now, it seems those are the only points that they put on. I'm going to put as many points as I can fit in my window range. Maybe that's all I can fit as well. But even if you wanted to use a table, build it around x equals 1. Meaning, if you're going to do 3 points to the right, use 2, 3, and 4. And 3 points to the left, use 0, -1, and -2. Don't go straight from 0 and off there, because you want symmetry and you want points that are reasonable within your window range. So you want to build around 1, which is exactly what you would do. Now, I'm not going to use a table, but I'm going to use my graphing methods and confirm, by the way, the y-intercept of 0, 5, confirm that the y-intercept hits what it does. The y-intercept is indeed 0, 5. So they say that because c is 5, the y-intercept is 0, 5, and because we can reflect across x equals 1, here we have that. And they promise to move faster. I'm just kind of giving you my intro stuff and how I'm going to do it, what it is that they're showing, and how it all interconnects. And what do they say up here? Be sure to include the negative sign before the fraction. Okay, yeah, okay. The domain, domain and range. The domain is all real numbers. This thing hits every value left and right. That's what I stated there. The range is based on basically your graph. Once you know where your vertex is and whether the graph goes upward or downward, then you know greater than or equal to that minimum value or less than or equal to the maximum value for y. In this case, y is greater than or equal to 2. 2 is the lowest value, and it goes up. Okay, let's talk maximum and minimum values. I just mentioned it, but let's see how they want to use it. I hope they do some word problems with it, honestly. They find them. Maximum value is the highest point on your graph. In this case, minimum value is the lowest point. Now, hear what I said with, and by the way, here's why I do like word problems for these. People forget on maximum and minimum, they feel like it's the ordered pair or the x value. The maximum or the min is the y value, the highest or the lowest value that we hit. And whenever we talk about word problems, when I say, how do I maximize profit? People start to understand better what we mean by that way, that it's actually specifically in reference to y. Anyway, so the y coordinate of the vertex of this is the max or the min based on whether it's an upside down facing graph when a is less than 0 or a right side up facing graph when a is greater than 0. Remember, a graph that goes down forever has no minimum. And that's the other confusing part. People think that, oh, it's going down forever. It must be minimizing itself, if that makes sense. No, it's going down forever. There is no minimum value. Whatever value you think is the minimum, I can go below it. The maximum is the highest that it goes because it goes down forever. There is no maximum when the graph is facing upward for the same reason. There's only a minimum. So there's that. Let's see what kinds of examples they give us here. Tell whether the function has a minimum or maximum value, then find the value. So they're going to state because a is a -4, this is an upside down facing graph. As an upside down facing graph, it means they have a maximum value. Now the value itself is the y value of the vertex. So how do we find that value? We find the x value of the vertex first. That's not the answer, but we find the x value of the vertex first using -b over 2a. So opposite of -24 over 2 times -4. Apparently it's -3. Let's just go with it. And then we substitute -3 into your equation. Boom, to boom, to boom. I'm still going to use these numbers. -3 squared is 9 times -4 is -36. -24 times -3 is positive 72. -36 plus 72 is 36. 36 minus 19 is 17. The maximum value is 17. It occurs at x equals -3, but the max value itself is 17. It's the y value of the vertex. It's the highest point that we reach for this upside down facing graph. Let's find a minimum value, and it looks like a word problem. So we have the Mackinac Bridge in Michigan form a parabola that can be modeled by this weird looking equation where, good thing I have a calculator out and handy for us if we have to use it. X and Y are measured in feet. So there's the parabola that they're using to talk about they're going to ask, what's the height of the cable above the water at its lowest point? They want to find, hey, where's that, what's the minimum height? And that's how you can kind of address, hey, this is a Y question. It's not an X question, but it's a Y. How tall is it? So we do find the X value here using negative b over 2a to go ahead and find, and they're rounding for us. I don't know if I would prefer rounding yet. I'm going to not round early, but 1,888 feet, which means 1,888 feet into the bridge, we're going to find our minimum, but the minimum itself, what's the Y? Substitute 1888 into here. I'm not going to find out what those are, but that's approximately 203 feet. 203 feet above the water is at its lowest point. Okay. Once again, some more examples for these ones here. This one would have a minimum because it's right side up facing graph. So that one would have a minimum. This one would have a maximum because it's an upside down facing graph. I'm not going to find out what they actually are right now. We're going to do them in the future problems. This would also have a minimum right there. Okay. Oh, I see what this is. I thought they were dancing. A group of friends is launching water balloons. The function. Oh, and here's where we actually get to, use graphs. I guess we did last time. But this negative 16t squared is the gravity thing, right? The function here represents the height in feet of the first water balloon t seconds after it is launched. The height of the second water balloon t seconds after it is launched is shown in the graph. Which water balloon went higher? So what they're having you do is decide what's the vertex of this one just by eyeballing it. Right, it goes a little bit above apparently 125, maybe about 130, and then you get to use your negative b over 2a on this equation and then plug in that t value into there to figure out which one has a higher y value. Not at what time it went higher or anything like that, which one just goes higher in general. So they say that, understand the problem. Okay, make a plan to compare the heights, represent both functions graphically. Oh, they say use a graphing calculator. I'm just going to use the vertex, right? Now, that being said, let's see what they do. The first water balloon only goes about 100 feet. So when you use your negative b over 2a here and plug in t, you're getting something close to 100 feet. Whereas the other one is above 125 feet, as like I said. So the second one's going to be higher. So they use a graphing calculator. You know, we're not assuming we're going to be using a graphing calculator in any sort of way. I'm going to talk more about the vertex stuff when I can. I have a graphing calculator, but unless the problem stresses that I should, I'm probably not going to necessarily. Not really the questions I want to focus on here. Okay, and let's go ahead and get into our vocabulary and core concept check. Let's explain how you can tell whether a quadratic function has a max or minimum value without graphing the function. A minimum value is when your graph faces right side up. A graph has a minimum value when facing upward. That's when a is greater than 0. And it has a maximum value when it is facing downward. When a is less than 0. It's all about a. Whatever a sign is. And a is never going to be 0 for a quadratic. So it's either positive or it's negative. Make sure you're actually in standard form in descending order of degree to know that it's the coefficient in front of the x squared. It's the quadratic coefficient. Consider the quadratic function f of x equals negative 2x squared plus 8x plus 24. Which is different? Find both answers. Which is different? What is the maximum value of the function? Let's say that's some a. Let's look at this. What is the greatest number in the range of the function? That would also be the same thing. The highest one up there, the maximum value. What is the y-coordinate of the vertex of the graph of the function? Yes, those are all the same, so this must be different. What is the axis of symmetry of the graph of the function? Yes, that is different. This is more with respect to the x value, right? I should, instead of saying a and b, I should really say y and x. But this is with respect to the x, this is with respect to y, and it's asking the same thing in different ways for that one. So it's this one that's different than the other ones here. They don't ask me to explain, so I will not. And that would be it there. Okay, guys, I'm going to get into the official problem set. This one's actually longer than the other ones. Let's see, it looks like it goes to number 49. So this is longer than the other ones. I don't know if the timestamp-wise it will be longer, but since I spent about almost 20 minutes with my lecture stuff, I gotta find a way to reduce those or speed these up. Let's go ahead and start moving forward. So I'm going to go ahead and pop this up as we see, and let's go ahead and get started. They didn't stress graphing as much. It looks like it's more about maxes and mins and vertexes. Maybe it will be a little faster. Maybe that's why they do that. Numbers 3 through 6, we're gonna find the vertex, axis of symmetry, and y-intercepts of these graphs. So I'm going to kind of like land on these graphs and show you what we're talking about. The vertex is going to be where we're, the minimum right here where it bottoms out. So when they say find it, they're just saying, tell us what it is. So this vertex here is going to be at 2, negative 1, also the minimum of the graph, if that matters to you. The axis of symmetry is the dotted line that we would draw that goes through the vertex here. It is an x equals equation. And it's important that we talk about this now because this is our first time that we're looking at quadratics that are not that are horizontally translating. We didn't even talk about descriptions. This is horizontally translating 2 units to the right, and vertically translating 1 unit down. But in this particular case, it's finally one where we're off the y-axis. So the axis of symmetry is at x equals 2. Once again, these should be the same. There's no reason those should ever be different. 2 for x on the vertex, 2 for axis of symmetry. The y-intercept of the graph is where we cross the y-axis. It looks like that is 1. So the y-intercept is 1. If you put either 1 or 0, 1, it all sounds good. I believe they did it just as a value. That makes more sense, but to locate the ordered pair is also good. Don't say y equals 1. That's an equation of a line, and that's not what this is. So that's number 3. So these ones go kind of fast, and I don't think I'm going to be doing a lot of the drawing dotted lines anymore here. I'll point to them, but that's it. Okay, number 4. So on number 4, right there, that is our vertex. That's at -3, 2. The axis of symmetry should be the vertical line that goes through there. That would be x equals -3. Sorry, I should label that axis of symmetry. And then the y-intercept, you can see it's crossing at -1 for y. And again, the y-intercept is something that we get to see in our equation. It's nice. It's actually in the equation itself, but furthermore, it gets us more points on the graph. And I think they are relying less on doing a table. It seems like when they ask us to graph, although I'm going to plot as many points as I can fit on my graph. But the y-intercept is a value that we can see in our equation. Number 5. Whereas the vertex does not. We have to actually calculate the vertex, and it takes a moment. So number 5, we have the vertex this time at -2, 0, and it's a maximum. The axis of symmetry is at x equals -2, and the y-intercept looks like it's at -3 this time. So the y-intercept -3. Okay, pretty quick problems. And number 6. Vertex at -1, 1. By the way, write your parentheses for ordered pairs. I don't know if that's stressed enough. Not writing them is improper. I know it kind of sounds like, what does it matter? It matters. It changes whether you're looking at an ordered pair or something else. Axis of symmetry is x equals -1. And the y-intercept looks like 5. And I bring that up because historically as I teach, there is one thing for me when I talk to you guys and I'm kind of saying all that you do right. Whenever I give you something and I say avoid it, main reason is because historically students do it. And it's weird because no matter what I ask students to avoid doing because of what I've seen from history and mistakes, students still do it. Maybe I've minimized the number of mistakes that people would have, but they still occur. Apparently it's human nature for students to do certain things with math. Missing parentheses could be among them. Oh, not writing x equals here could be among them. Things like that. All right, next exercise is 7 through 12. We're going to find the axis of symmetry and vertex of the graph of the function. We are not actually graphing these functions. At least it doesn't look like not until number 13. So on number 7, we have f of x. f of x equals 2x squared minus 4x. In order to find the vertex, axis of symmetry is going to be the same thing. In order to find the axis of symmetry, we are going to be finding the x equals equation, x equals, and we're going to be using -b over 2a. As far as this equation goes, this is right now ax squared plus bx plus c. You can tell that there is no c that's here. That means it's plus 0, and that's not going to matter for our stuff here, but it matters to identify b and a. b is -4. a is 2. When we say -b over 2a, we don't say, well, 4 is already negative, so let's just keep it negative. No. -b over 2a is the opposite of b over 2 times a. So the opposite of -4 is +4, and 2 times 2 is 4. And 4 divided by 4 is 1. X equals, I should write x equals 1. It's kind of saying that, but let's do that again. X equals 1. X equals 1 is your axis of symmetry. Excuse me. And it's also the x value of your vertex that we use to find the vertex. It's the x value that we use to substitute into the equation. So to find the vertex, f of 1, let's substitute 1 into there. That's 2 times 1 squared minus 4 times 1. 1 squared is 1. 2 times 1 is 2 minus 4, and that's -2. Now, there's something I'm going to bring up later with respect to the vertex, finding the y value. I've done it every single time so far in the lecture portion where I've been computing and calculating what it is. And I wonder if you've seen the pattern. If not, I'll run through a couple more and see if you can pick up on a pattern on what happens when I'm doing some calculations here. You're going to have to hear it. You're going to have to hear some of it, though. Now, I bring it up because some problems might be out of reach large or fractions or something later. Okay, number 8. Y equals 3x squared plus 2x. Once again, there's no actual c value. This time it says just y equals, though. So 3x squared plus 2x. A is 3 and b is 2. For the axis of symmetry, x equals negative b over 2a. That's negative 2 over 6, which is negative 1/3 when reduced. So x equals negative 1/3. Again, I feel compelled to put x equals straight up, otherwise you might misconstrue for the equation. Now let's take f of negative 1/3. Let's find the y value at this x, which I'm glad I'm not actually graphing this one, because that's a nightmare to graph something with a fraction bit. And I'm sure they're going to throw on one on with us to graph, but you know what? For now, I'm glad I don't have to. But I do have to compute this. This is 3 times negative 1/3 quantity squared plus 2 times negative 1/3. And I'll let you know right now, I think after this one, I need to reveal kind of this pattern that I'm talking about here, because otherwise it might be a nightmare for you to work off of, unless you're using a calculator plugging things in, but I want fraction answers when need be. Negative 1/3 squared is 1/9. Let me first write this out, is 1/9. I'm going to do 3 times 1/9, and 2 times negative 1/3 is negative 2/3. Negative 2/3. Oh, this one might clean up. Oh, not quite. 3 times 1/9 is 3/9. 3/9 is also 1/3. So we have 1/3 minus 2/3, which is negative 1/3. So the vertex is at negative 1/3 for x and negative 1/3 for y. They are the same thing. Now that's not the pattern, nothing about them being the same. But have you guys noticed, and you'd have to go back to some of the notes here, but take a look at this pattern here. There was no c on these ones, but when you find the x value of your vertex and we substitute them in to find the y value, the first term plus the second term will combine to become the opposite of the first term. I don't know if that makes sense, but 2 minus 4 is negative 2. 1/3 minus 2/3 is negative 1/3. It's going to become the opposite of that there. And I bring that up because if the numbers get strange, if you're not sure how it works, you're going to hear me compute that one really fast before I do the plus c portion of it, because you're just swinging around to change the sign. And it's a pattern, but that happens for the x value of the vertex finding the y value when you do the ax squared plus bx. And there's a reason behind it. When you plug it in, you'd actually see. But you know what? That's what it is. That is number 8. Number 9. Y equals. This one has a c value. Y equals. Oh, I don't want blue. Negative 9x squared minus 18x minus 1. All right, for the axis of symmetry, x equals negative b over 2a, opposite of negative 18, over 2 times negative 9. A lot of negatives, but 2 negatives make a positive, and then 2 times negative 9 is negative 18. We get negative 1. So x equals negative 1 is the axis of symmetry. For the vertex, the y value, f of negative 1. So we have negative 9 times negative 1 quantity squared minus 18 times negative 1 minus 1. Negative 1 squared is 1 times negative 9 is negative 9. Now you have negative 18 times negative 1 is plus 18 and then minus 1. Here's where, like I said, these two will combine. Negative 9 plus 18 is positive 9. These two combined together will be the opposite of whatever that a value was after you plugged in your x from the vertex. So negative 9 plus 18 is 9. Like, boom, just kind of switch that sign. It's almost not worth even writing what you're plugging into here just to do that. Anyway, 9 minus 1 is 8. So the vertex in this case is negative 1, 8, like that. And I'm off the page, but let's go and move on to number 10. All right, number 10. f of x equals negative 6x squared plus 24x minus 20. Okay. Yeah, it doesn't look like we're probably doing a lot of graphs. Maybe that's what'll go a little faster here. But we're doing this whole negative b over 2a bit each time. The axis of symmetry, x is negative b over 2a. That's negative 24 over negative 12, which is positive 2. That gets you x equals 2 as your axis of symmetry. For your vertex, your y value is going to be f of 2. We'll do negative 6 times 2 squared plus 24 times 2 minus 20. 2 squared is 4 times negative 6 is negative 24. Anyone know what negative 24 plus 48 is? That's right, 24. 24 minus 20 is 4. That's the y value. So you have a vertex of 2, 4. I wanted to make sure we weren't supposed to do anything else here. That's it. Okay. Because otherwise I'm like, shoot, I have to go back to 7, 8, and 9 if they were asking about domain and range or something. Number 11. Look at this fraction. Let's go. Number 11. F of x equals 2/5 x squared minus 4x plus 14. The axis of symmetry exists at x equals negative b over 2a. Oh my goodness. What am I going to do for 2a there? The opposite of negative 4 is 4, and we're dividing by 2 times 2/5. That is 4/5. Now, when you, let's put equals. When you divide, it's 4 divided by 4/5, which is also 4 times 5/4. 4 divided by 4 is 1. 1 times 5 is 5. So that's the axis of symmetry is x equals 5. Crazy, right? Okay, x equals 5. The y value, at least it was clean, right? Now the y value, we're going to take f of 5, and we get 2/5 times 5 squared. This will clean up. Minus 4 times 5 plus 14. 5 squared is 25. 25 divided by 5 is 5, times 2 is 10. We're going to get 10 for that. Minus 20 plus 14. 10 minus 20 is negative 10. And negative 10 plus 14 is positive 4. So our vertex is at 5, 4. And it's a minimum because the graph faces upward because a is positive. Number 12, another fraction to begin with. We get y equals negative 3/4 x squared plus 9x minus 18. Notice how they interchange f of x with y, but each time I'm still using f of regardless when I substitute the thing in. That's okay. Axis of symmetry. Axis of symmetry, x equals, once again, we have to deal with this fraction bit. Negative b over 2a, negative 3/4. Boom, boom. That's a negative 3. So that's negative 9 over negative 6, let's see, negative 3 halves, right? 2/4 is 1/2 times negative 3 is negative 3 halves. Now, negative divided by negative is a positive, so I'm going to ignore the negatives here on out. But this is 9 divided by 3 halves, which is 9 times 2/3. 9/3 is 3. 3 times 2 is 6. So the axis of symmetry is x equals 6. As far as the vertex goes, let's do f of 6. And we're going to get negative 3/4 times 6 squared plus 9 times 6 minus 18. On the same token of what I stated on, like, you know, it's the negative here and plus and it changes sign, we could just take half of whatever this is. I'm going to tell you this. These will combine to equal 27. I already know that, but let's compute it. 6 squared is 36. Divided by 4 is 9. Times negative 3 is negative 27. What's negative 27 plus 54? Well, that's 27. 27 minus 18 is 9. So we get 9 for the y value of the vertex, and we get a vertex of 6, 9. Giggity. Not my best impression. All right. So that is number 12. All right. Numbers 13 through 18. Let's graph the function. Okay, and describe the domain and range. So now we're getting pretty serious. Let me find one of my graph axes. And, you know, I'm not using my taller graph axes that I generally would use. I gotta probably go back and do those at some point. But you know what? Nah, we're good. I'm going to shrink these to size because I got to do some vertex work, right? I got to get that vertex. Okay. F of x equals, number 13, f of x equals 2x squared plus 12x plus 4. Okay, now it's of no benefit to you. I'm thinking like greatest common factor. It's no benefit of us to use a greatest common factor here. We're not doing anything like that. For the vertex, let's find the x value. The x value is going to be negative b over 2a. Negative 12 over 4, which is negative 3. There's the x value of your vertex. For the y value of the vertex, we find f of negative 3. 2 times negative 3 squared plus 12 times negative 3 plus 4. Negative 3 squared is 9 times 2 is 18. Minus 36 will be negative 18 plus 4 is negative 14. Uh-oh. I need a taller graph. Okay, I'm going to pause this. Give me 1 second. Okay, and I'm back. Sorry, I had to put my foot in my mouth there when I was going to, like, I don't have to use tall graph paper. Yes, I do. So I'm putting this one in. So negative 14 is the y value of the vertex. Okay, so I guess we got to use these. So I'm going to plot as many points as I can fit. This thing's probably going to say, oh, you put just this and that. No. We're gonna go as tall as we can here. So negative 14 is that. So this vertex is at negative 3, negative 14. When it comes to graphing, a is greater than 0, or it's positive, I should say, and this is therefore a minimum. So at negative 3, negative 14, we are right there. That's the bottom. Now, they are going to ask us to graph. Is that it? And describe the domain and range. Now, as far as the graph goes, there's another point on this graph that I can use, and it has to do with the y-intercepts right here. This 4. Boom. Right there. 0, 4 is the y-intercept of this guy. That's a point we can use. And furthermore, but furthermore, there's an axis of symmetry at x equals negative 3. Whether or not you draw it, note its existence, because there's an axis of symmetry right here. It's a pretty thick one. I laid it on. Let me thin it out. This axis of symmetry that reminds us that points reflect across here. So not only is there 0, 4, but there's this guy, negative 6, 4 is another point in this graph. Now, this graph is some parabola, but I'm going to find more points on this thing, not by table, though if you did, you would substitute x values left and right of negative 3, so negative 2, negative 1, and like that. But I'm going to use my vertical stretch factor of 2. So instead of over 1 up 1, over 2 up 4, over 3 up 9, we're going to double those values. Instead of 1, 1, we'll go 1, 2. Instead of 2, 4, we'll go 2, 8. 5, 6, 7, 8 up from there. And I can reflect those points across here and here. Instead of 3, 9, we're going to go 3, 18. Well, what's 18 up from negative 14? Oh, it's 4. So there's that point. We got that one. And instead of 4, 16, we'd go 4, 32. I can't quite fit 32. It's actually really close. What's 32? What's negative 14 plus 32 is 18. So actually it would have gone right here. That's reachable. So I'm going to plot that one as well. This is going to be a tall graph, yo. And I did that pretty much at the drop of a hat when it came to, I'm not using a table. You know what my problem is? I don't think I can draw this straight. Not with this stuff. So apologies. This isn't going to be the best looking curve, despite the precision from all the points that we have. Okay, I'm going to attach this graph paper and this stuff. I'm very sorry about that. Woo! Yeah, no. Okay, that makes it look a little bit nicer. Describe the domain and range. Describe the domain and range. Your domain, I'll keep this in blue. Your domain is all real numbers. This is going to go forever left and right. Your range, and by the way, we could have done this stuff without drawing the graph, but this graph will remind us on what it is. Your range, the graph goes upward. The lowest point is negative 14. Y is greater than or equal to negative 14. There's your domain and range for number 13. Okay, let's move on. Number 14. And they're going to make these sharp. Oh my gosh, they're going to make these sharp. No wonder. They really want to emphasize just that y-intercept, I bet. I don't know why, but I guess that's their deal. I'm going to put this up early just in case. Well, not just in case. We got to use it. Number 14, we have y equals 4x squared plus 24x plus 13. My, oh my. What is our vertex? Our vertex is x equals negative b over 2a, which is negative 24 over 8, which is negative 3. Your y value for that, f of negative 3. 4 times negative 3 squared, 9 times 4 is 36. We're going to get negative 36 plus 13. Plus 24 times negative 3 is negative 72. 36 minus 72 is negative 36. Plus 13 is negative 23. I can't even fit this on this graph. I have to scale by 2s. I forgot what I said it was. Negative 23? Negative 23. No, I can't even fit this. So I'm going to have to scale by 2s on this one, y'all. Vertex is negative 3, negative 23. So, yeah, let's go by 2s on y. On x's, I'm going to keep them the same. So, negative 10, negative 20, negative 30, and 10, 20, 30. Okay. 13 is the y-intercept as well. We're going to talk about that, y-intercept. So we're going to plot some points. Oh, yes, we are. So let's see. I shouldn't use blue. Let's see. Let's use black on these. Okay. Hopefully you can still see that. So, negative 3, negative 23. My x is still going by 1s, okay? Maybe I got to write that. Sorry, didn't plan for this. Negative 5 and 5. Okay. We got negative 3, negative 23. So here's negative 20, negative 22, negative 24. Negative 23 is going to be right in the middle right there. Now, your y-intercept is 0, 13, 2, 4, 6, 8, 10, 12, 13 there. The axis of symmetry is right here, so I'm going to go 3 across and another 3 across and get that one at negative 6, 13. There's that point. Now, the vertical stretch factor is 4, so we're going to go over 1, up 4, 2, 4, like that, instead of 1, 1, and reflect that. Instead of over 2, up 4, it will be over 2, up 16, because 4 times 4. 4, 8, 12, 16. I need to be really careful. I think that's correct on that one. 3 over, well, we're going to hit this. How come? Because 9 times 4 is 36, and we're going to go up 36. Negative 23 plus 36 is indeed 13. Boom. And 4 over 16 times 4 is 64. Can I fit 64, 30, 34? I can't fit 64. So I'm going to go ahead and keep it at that. And let's go ahead and draw that guy. Try and curve it as much as you can. Try and not V it at the bottom. I know that it might naturally get some of that V shape because of just how straight, just how steep it is. I'm just going to end it like that. That's fine. All right. Domain, all real numbers. Range, y is greater than or equal to negative 23. Please don't do that to me again. I already got myself a tall graph. I was supposed to do this and help us out. Let me keep this like this. I want to keep this side busy. Number 15. Number 15. Y equals negative 8x squared minus 16x minus 9. All right, well, this graph goes upside down. To what extent? 8x squared minus 16x minus 9. Okay. Vertex. The vertex, the x value is negative b over 2a. Opposite of negative 16 is positive 16 over negative 16 is negative 1. I like when it hugs close to there. I think this is going to be 17. No, negative 1. I think the y value is going to be negative 1. The f of negative 1 equals negative 8 times negative 1 squared minus 16 times negative 1 minus 9. That'll give us negative 8 plus 16, which is positive 8, minus 9 is, yeah, indeed negative 1. So your vertex, oh, I need to give myself some room. Your vertex is going to be at negative 1, negative 1. So I don't need the top part of this tall graph, but I sure need the bottom. I don't think I need the right side either, so I'm going to go ahead and cut this off over here. So negative 1 is the vertex. The y-intercept is negative 9. So 0, negative 9 right there. And across the axis of symmetry, 1 away, over here is this other point. This is really all I'm going to be able to get. This is one of those where, even as the book would say, it's like, don't worry about a table. You have enough points as it is. I don't like 3 points for a parabola myself because of, I want to really get into the fact it's not a V shape. You don't just go down 8. Oh, I didn't even do negative 1, negative 1. I'm sorry. I just did negative 1, 0. Whoops. Negative 1, negative 1. There we go. I was thinking that seemed like more than 8 away. I was actually thinking about that. It said that looks a little low. All right, but anyway. It's not just a V shape, but it's going to be hard to kind of tell one way or the other. It does go steep, absolutely. This domain, guys, it's still all real numbers. Just because it goes steeper doesn't change the fact that you can still substitute anything for x that you'd like, and you'll still get a y value out. Range, it goes down forever from negative 1. Y is less than or equal to negative 1. That's your range. And then number 16. Oh, and 17 and 18. They're just on the other side of the page. It says for 13 to 18. And then, number 16, we have f of x equals negative, I wonder how extreme they get next. Negative 5x squared plus 20x minus 7. Okay, so for this one, the x value of the vertex is at negative 20 over 2 times negative 5, which is negative 20 over negative 10, which is positive 2. Yes, positive 2. The y value for that will be, negative 20 plus 40, which is 20, minus 7, which is 13. So your vertex is at 2, 13. 2, 13. Okay. 2, 13 vertex, and 0, negative 7, or negative 7 is your y-intercept, okay? So, let's see. 2, 13, all the way up there. I guess I'm glad I did the tall graphs. I guess I'll do tall graphs for anything I do here on out. I can't anticipate what else they're going to use. 0, negative 7 is a y-intercept. I'll find that naturally anyway, right? Oh, and reflect this point as well. Over 1, we're going to go down 5 because 5 times 1. I just can count. 1, 2, 3, 4, 5. Over 2, 4 times 5 is 20. We go down 20 from 13, which is negative 7. So that worked out. So we reflect that across, and that's really all I can fit. I'm going to go ahead and sketch it from here. That's okay, son. We'll sketch it from here. Or good work, son. Good work, boys. We'll take it from here. Okay. Sorry, I have to find a way to occupy my time while I sketch that guy. It's really hard to do, and I think it really messes up my stylus when I do that. It's that hard work. Domain and range. Can't skip that. Domain, all real numbers. Range, y is less than or equal to 13. 17 and 18. Oh, that's what they have. Duh, fractions. Where we might not have to go as tall, we'll see. Numbers 17, 18. Here we go. Y equals no, not negative. 2/3 x squared minus 6x plus 5. Okay. Vertex. X value is negative b over 2a. Positive 6 over 4/3. That also means 6 times 3/4. This is still a fraction, so that's not going to be fun for the graph. But 6 times 3/4 is 9 halves. 9 halves. So the x value is 9 halves. That might get cut off by my graph. The y value. No. is 9 halves. The y value, f of 9 halves. I know you guys don't like fractions. I know. It's okay, though. It's okay. 2/3 times 9 halves squared minus 6 times 9 halves plus 5. So 2/3 times, oh boy, 81 fourths minus, so okay, this is where this will be helpful. If I didn't want to do this, what's this calculation? Oh my gosh, which is actually not bad. I can do some division parts. But 6 divided by 2 is 3. 3 times 9 is 27. Oh, it's still a fraction though, darn it. It's 5. Remember, whatever this is going to be half of what that is, because half of this minus 27 will bring this to the other side. So what's half of 27? 13 and a half, or 27 halves, right? So half of 27 minus 27 is going to be half of 27, negative 27 halves. So negative 27 halves plus 5. So 5 is 10 over 2. I'm going to stick as fractions. This is negative 17 halves. So, okay, your vertex is at the great value of 9 halves comma negative 17 halves. Now that's also 4.5 and negative 8.5, which I guess would matter for your graph. So let's go ahead and cover that all up. Let's go ahead and graph this. 4.5, 1, 2, 3, 4.5 is the x. Negative 17 halves, negative 8.5 is the y, negative 8.5. Kind of like a right in the middle there. This thing means nothing. This one will be harder to state the points because not only, oh my gosh, it really will be. Even with the table, plugging in values, nothing about this one is going to be fun with regard to getting extra points on the graph. I'll see what I can do, but we do know that there's a y-intercept of 5, which is really crucial to this thing because you could at least get this point one that reflects across. What are we reflecting across, by the way? We're reflecting across x equals 4.5. So that one's weird, right? We're reflecting across this. So what's 4.5 away from, what's 4.5? There we go. What's 4.5 halfway from? Halfway between, 4.5 is halfway between 0 and what? 9. I'm sorry that I can't speak. 5, 6, 7, 8, 9. So there's another point. So I'm sure they'll just say, hey, draw the parabola. Over 1. Up 2/3 of 1. I don't know what 2/3 up from a half is. Kind of like that. Over 2 up. Yeah, I'm not going to do that. That's quite a bit. All right. We'll deal. We'll deal. It's not so bad if I was just doing a fraction, but a fraction off of a fraction without writing it down is a no-go for me. I'm not going to spend more time on it if the thing wouldn't decide to do it as well. But it is still a curve. It's not as much a V as it is a U. But you notice, without other points, I'm not giving myself my best U that I think I could do. My best U. Number 18. Probably just as troublesome. Maybe. The stretch factor itself is a little nicer, being a 1/2. But it is negative. That's okay. Number 18. We have f of x equals negative 1/2 x squared minus 3x minus 4. The x value of the vertex is x equals negative b over 2a. Yeah, this looks a little better. Opposite of negative 3 is positive 3. 2 times negative 1/2 is negative 1, and that gets you negative 3. Oh, that gets you negative 3 as an x value of the vertex. Now let's do f of negative 3, which is negative 1/2. I'll tell you what, if your teacher says do 1 through 17 odd, you're like, wish I had 18 as I wish I was 2 through 18 even. Negative 1/2 times negative 3 squared minus 3 times negative 3 minus 4. Now we're still going to have to deal with a fraction on this part. So negative 3 squared is 9 times negative 1/2 is negative 9 halves plus 9 minus 4. Mr. Robinson, what's negative 9 halves plus 9? Positive 9 halves, right? You take half of 9 and go the opposite direction. So 9 halves minus 4. 4 is 8 halves, and that gives you 1/2. Still better looking numbers as far as what we're going to do. It's still a fraction. But negative 3 comma 1/2 is the vertex. Oh, I didn't do domain and range in the last one. Give me 1 second. Domain, all real numbers. Range, y is greater than or equal to negative 17 halves. Okay, now this one. Negative 3, comma, 1 half. Okay, and a y-intercept of negative 3 over here. All right, I'm fine probably trying to plot a lot of these points. I don't like the 1/2 nature, but from where I'm from, but I'm good with it here. When you go over 1, we're going to go down half of 1, like that, boom. Over 2, down half of 4, so right, so 2, like that. Over 3, down half of 9. Now half of 9, oh wait, that doesn't work. Oh, negative 4, I'm sorry, negative 4 is the y-intercept, not negative 3. There, that does work. Ah, see, I want to use a y-intercept to confirm what I do. Over 3, down half of 9, that's 4.5. So half, 1.5, 2.5, 3.5, 4.5, just like that. And I'll just keep moving. Over 4, down half of 16, which is 8. So, what, 7.5, I guess? Negative 7.5, negative 7.5 right there. Wait, negative 7.5. Over 5, down half of 25, so it's 12.5. So 12.5 is going to be negative 12. And over 6, down half of 36. I don't think that'll fit at 18. Oh, negative 17.5. It'll just be off like that. Okay, and I do want to reflect these points across. I will draw my axis of symmetry on this one. The princess will marry me. All right, let's just reflect those across. So, boom. I'm trying to really squint and get these right. Is that height right there? And there. That one's pretty. That one's good. Look at that. Waterfall. Boom. Boom. Tell a table to get those points that fast, huh? All right, domain and range. Let's not forget those before we move on to the next section. The domain. Le domain is all real numbers. The range is going to be y is less than... What the heck did I just do? The range is going to be y is less than or equal to 1/2. Okay, that is graphing those. I probably don't have to do much graphing after that, which is cool. But we are going up to number 49. All right, maybe we do have to do some graphing the word problems. Let's see. Numbers 19 and 20, error analysis. Describe and correct the error in finding the axis of symmetry of the graph of y equals 3x squared minus 12x plus 11. So your a value is 3, your b value is negative 12. For negative b over 2a, common rookie mistake. Negative 12 is your b value, so we got to take the opposite of negative 12. This negative still exists outside of the negative 12, like so, and you take the opposite of negative 12. Classic rookie mistake. All right, so how do we say that? When applying negative b over 2a, the b value was already negative and not taken opposite of. If that makes sense, right? You don't just say, oh, there's a negative in the form, or like, the negative b, and go, oh, b's already negative, so I'll just leave it negative. No, everything, it's not negative b over 2a. I say that, but it's the opposite of b over 2a. Makes sense? Technically, it's the opposite of the fraction, but I apply it to the numerator. So let's go and fix that. I mean, everything's going to be the same except putting a negative, which just changes the sign. So the x value, the vertex, will be negative b over 2a, which is negative, or the opposite of negative 12 over 2 times 3, which is positive 12 over 6, which is 2, positive 2. Axis of symmetry. Whoops, x equals 2. Okay, that's number 19. And that's good that we call that thing out, right? That's something that is missed often. Number 20, error analysis. Describe and correct the error in graphing the function f of x equals x squared plus 4x plus 3. I can tell you one thing. It shouldn't be upside down. Let's see what they do with that. So they find the vertex at b, b over 2. Well, I mean, I guess that's part of the problem. In fact, that's why it goes upside down, right? They didn't make it go upside. They didn't say let's graph this upside down. They got a vertex value that was above the y-intercept. So they said naturally it's got to go down to fit it. So their problem is not just that the graph's upside down. Their problem stems way earlier, and it's that they use b over 2a, not negative b over 2a. This is going to change everything, though, so I have to redo the entire problem as a result. I assume I would have anyway. But everything after that, it's the first mistake. The first part was the mistake, basically. They used b over 2a instead of negative b over 2a. To find their x value of their vertex. This consequently gave the wrong vertex a y value that was above their y-intercept and an upside down parabola when a was greater than 0. Oh my goodness, when a was positive. So, there's all that. Let's fix all that. I'm just going to use this blank space down here if that's cool. So, let's go again. Play it again, Sam. The vertex. The x is negative b over 2a. So look at the problem. The b is 4. So negative 4 over 2 times 1. The a value there is 1, right? Negative 4 over 2 is negative 2. So now the x value is negative 2 for the vertex, but the y value, more importantly, is going to also change. Negative 2 squared plus 4 times negative 2 plus 3, which is, let's just kind of do this mentally. 4 minus 8 is negative 4, plus 3 is negative 1. Way different. Vertex is at negative 2, negative 1, instead of 2 comma 15, right? So negative 2, negative 1, and listen, I'm not going to go deep with this graph. Where's the old graph paper? Hold on. Trying to select this thing. There we go. There it is. Sorry about this. It's a little rough. Facing some technical difficulties, folks. I got small spaces to work with. All right. Negative 2, negative 1 is here. And then 0, 3. 0, 3 is the y-intercept. And this makes sense. The vertical stretch factor is 1. Over 1 up 1. Over 2 up 4. Over 3 up 9. And we can reflect those, including especially the y-intercept we could have found before. That's what your graph should look like. Whoops. Right here. All right. There's the graph. There's the fix. That's all I have to do. Okay. Numbers 21 and 26. Tell whether the function has a minimum value or a maximum value, then find the value. Okay. For these problems, we saw these in the notes as well, the lecture portion, not the notes, the lecture portion as well. So y equals 3x squared minus 18x plus 15. We've been kind of doing a lot of this already. I didn't write whether it was a minimum or a maximum, but I either said it or I graphed it as such, right? So what we do is the minimum or maximum occurs at your vertex. So we are going to have to find the vertex, more specifically the y value. The y value is based off the x value, though, so we have to do that anyway. It is a minimum if the graph faces upward. It faces upward if a is positive. This has a positive a value, so this is going to have a minimum. So it says tell whether it has a minimum or a maximum. 3 is greater than 0, right? A is 3, which is greater than 0, so it has a minimum. And I just want to state one more time, it goes upward, and so people think up means maximum. No, upward means it has no maximum. It goes up forever. It bottoms out. It bottoms out, therefore it has a minimum. So what is the minimum? First, we got to find the x value of the vertex. And that is negative b over 2a. That's 18 over 6, which is 3. The y value, therefore, is going to be 3 times 3 squared minus 18 times 3 plus 15, which is 27, minus 54, which is negative 27, plus 15 is negative 12. Okay, now this is the minimum. The minimum is negative 12. It's the y value when it comes to the vertex being 3, negative 12, negative 12. Once again, I'm just going to highlight it wherever I go, is the minimum. It occurs when x equals 3, but the minimum is at negative 12. Okay, I'm not graphing it. They didn't ask me to. Number 22. F of x equals negative 5x squared plus 10x plus 7. Now I mentioned that a graph has a minimum when it's right side up, when a is positive. It's upside down, or excuse me, it has a maximum when it's upside down, when a is negative. This a is negative negative 5. Negative 5 is less than 0. This has a maximum. If only I could handwrite this stuff. Where is that maximum? The vertex is at x equals negative b over 2a, which is negative 10 over negative 10, which cancels out. No, which is 1. God, for every time my students say cancels out as if things magically go away. The y value, we take f of 1, which is negative 5 times 1 squared plus 10 times 1 plus 7. That's negative 5 plus 10, which is 5, plus 7, which is 12. That is the maximum. The minimum was negative 12. The maximum is positive 12. Remember, this vertex is at 1, 12, but 12 once more is the, 12 is once more the maximum value. It occurs when x equals 1. So maximum. I guess I'm going to write that each time. I'll just go and draw those arrows and stuff just to be consistent. Number 23. F of x equals negative 4x squared plus 4x minus 2. This has a maximum. It has a maximum. We'll find out what that is in just a moment. The x value of the vertex is negative b over 2. By the way, it has a maximum because it's a negative upside down graph. Negative b over 2a, which is negative 4 over negative 8, which is positive 1/2. Now, I shouldn't be boxing those. That has nothing to do with my answer. But it's the end of the line, though. But f of 1/2 now is negative 4 times 1/2. What did I just do? Negative 4 times 1/2 quantity squared plus 4 times 1/2 minus 2. 1/2 squared is 1/4 times negative 4 is negative 1 plus 2 is positive 1 minus 2 is negative 1. Negative 1, which is the maximum. We have a maximum of negative 1. Okay, that's how I'll write it from here on out. There's a maximum of negative 1. Like that. Number 24. Number 24. Y equals 2x squared minus 10x plus 13. Folks, will this have a minimum or a maximum? Yes, a minimum. Okay, this will have a minimum given that it's a right side up facing graph. Let's find the x value of the vertex. Negative b over 2a, which is 10 over 4, which is 5/2. Please get in the habit of understanding your fractions, though, right? Less calculator work, the more savvy you are with this in total. No 2.5s. No 2.5s. 2 times 5/2 squared. Do you know 2.5 squared? Because you know 5/2 squared, right? You might. I know 2.5 squared. Times 10. Minus 10 times 5/2 plus 13. 5/2 squared, 25/4. See? 2 times, so 50/4, so 25/2. Minus 50/2, which is negative 25/2. Plus 13. Negative 25/2 plus 13 is 26/2 is 1/2. And that is the minimum. The minimum value is 1/2. It only goes up from there. So that is the y value, the smallest y value that it hits. It occurs when x equals 5/2. 2 more, and of course they hit the fractions, so let's check those out. Number 25. Number 25, we have y equals, oh, what happened? Y equals negative 1/2 x squared minus 11x plus 6. Negative, it is a maximum. Let's find the x value of the vertex and use it to find that y value. So the x value is negative b over 2a. 2 times negative 1/2 is negative 1. We have positive 11 over negative 1, which is negative 11. For that 1/2, freaked me out for a second, but we get that. We'll probably get a fraction here. It looks like it. So f of negative 11 will be negative 1/2 times negative 11 quantity squared minus 11 times negative 11 plus 6. So negative 1/2 times 121 plus 121 plus 6. Let's make no two bones about it. This half of 121 and then added is positive 121 over 2 plus 6, which is 12 over 2, which becomes 133 over 2. It's a beautiful number. It's my favorite number. Coach, can I get a jersey number of 133 over 2? That's the maximum. That's where it tops out at. 133 over 2 is also 66.5. I hope I didn't screw anything up there, but yeah, sure. It makes sense to me. There it is. All right. Number 25. Let's go to 26. Number 26. We're now halfway done. How long have I gone? Oh, this is going to be a long one. F of x equals 1/5 x squared minus 5x plus 27. The 1/5 being positive means we will have a minimum. Let's find the y value of the vertex in doing that. The x value is negative b over 2a. Sorry about that. Which is 5 over 2/5, which is 5 times 5 halves, which is 25 halves. 12.5, 25 halves. Now we are going to find the y value of the vertex. F of 25 halves is 1/5 times 25 halves squared minus 5 times 25 halves plus 27. Torture. Let's go. 1/2 of 625 over 4. That's 25 squared, and that's 2 squared. 5 times 25 is 125, so minus 125 halves plus 27. So check this out, right? I have 625. Does that look right? 625 over 8 minus 125 halves. Suddenly, I am questioning something. I want to pause and confirm I have everything right, because normally this would just be like negative 125 fourths or something like that. Maybe something went wrong. Let's take a look. Okay, that was the quickest pause in the world. This is not a 1/2. This is a 1/5. 1/5. There we go. Okay, now check this out. 625 over 5 is 125. That's where your 125 fourths comes from. And here's the thing. You know why I knew that it should have been 125 fourths? Because this should be half of this number. So that pattern actually saved me because I copied something down wrong. That should have said 1/5 the whole time. So there, that saved me. Now, guys, what's 125 fourths minus 125 halves? It's negative 125 fourths. Once again, it's just the pattern. That's what's just going to happen. It kind of makes things easier to work off of. Now, 27 is also 108 fourths. And that is going to give you negative 17 fourths. Okay, so I think that should now be good. We have a minimum of negative 17 fourths for y. That's the final answer there. Okay, yeah, don't just copy down what I put, please. I make mistakes all the time, guys. I really do. Especially, or when I talk over it, I do. Things just happen. Okay, we're diving into the word problems. So let's go into those. Let's see how often we have to graph. A lot of vertexes, I'm sure. Number 27. The function shown represents the height h in feet of a firework t seconds after its launch. The firework explodes, at its highest point. At its highest point, when does the firework explode? So notice this word problem, first of all, this is h equals negative 16t squared plus 128t. I think I think even the lecture portion of this thing kind of said, like, step one, understand the problem, or something like that. So understand this. Time happens, right? Now the firework doesn't have to go this way. It probably just goes straight up. So it goes straight up as time goes on and explodes at the top. It says, when does the firework explode? It's at the top. But not what was that height. I'm sure that's the next question. The first question is when. T is like your x now. We have to find highest point, vertex, the x value, or the t value of your vertex. So for the vertex, the t value is negative b, and this is your b, negative 128, over 2a, 2 times negative 16. Negative 128 over negative 32, and I believe that's 4. So 4 seconds after it's launched, it explodes. That's the t. Next question, at what height does the firework explode? Now, so this is part A. Now part B is going to be, we got to take h of 4. So substitute 4 into here, find out the thing. That's the maximum. At what height? So notice it's the y value, or in this case the h value. So negative 16 times 4 squared plus 128 times 4. 4 squared is 16 times negative 16 is negative 256. Without calculating that, I could tell you this answer will be positive 256. That being said, 128 plus 4 is 512, and negative 256 plus 512 is positive 256, and that is the feet. Remember, vertex, the A plus the B is the opposite. Okay. Let's go. Number 28. Modeling with mathematics again. The function h of t equals negative 16t squared plus 16t represents the height and feet of a horse. Sorry that I stopped talking. I was going to say something, and I will still say eventually. Of a horse t seconds after it jumps during a steeplechase. When does the horse reach its maximum height? Can the horse clear a fence? Ooh, good question. If so, by how much? How long? I thought it said how long is the horse hair. How long is the horse in the air? Interesting last question, and something we'll talk about here in a moment. Okay. I forgot what I was going to talk about. When did I stop talking? I said of a horse. Two independent people who I know, for some reason, I do Family Guy impressions. So I was like, oh, hey, Lois, how's it going? Whatever. And sometimes I'll randomly do it in just a moment. Like, all right, so what? And they're like, oh my gosh, that sounds like Peter. And then, so like I coach softball, which are females. And then there was another group of females as well, I think my students, where two of them independently said like, oh, I can do a good Lois. Now, I can't do a good Lois. Like, hi, I'm Lois. Whatever. I can't do it. But they both actually do pretty good Lois things. And their line that they say, this must be on TikTok. I'm going to look it up after this video. This must be on TikTok, where they're like, I can do a good Lois, and they say, Peter, the horse is here. And they go, Peter, the horse is here. Whatever, however you do the Lois. So I was just thinking of that, like, height of a horse. Peter, the horse is here. Anyway, I was going to say that, and that was the thing. Let's do some math. But I'm going to look that up. That must be somebody who's imitating Lois on TikTok or something, and they say, Peter, the horse is here. And I think that's from a specific Family Guy episode. Anyway. Let's move forward. H of t equals negative 16t squared plus 16t. Okay, here's a horse. Height. After t seconds. Leaping in the air during a steeplechase. Okay, when does the horse reach its maximum height? That's just asking for t for the vertex. So part A, the vertex t value is negative b over 2a. Negative 16 over negative 32, which is positive 1/2. So half a second later, or after 0.5 seconds, you'll notice I tend to go to the decimal or the actual straight up division with a word problem. You're going to see that quite often from me, because we don't, I guess we say half a second, but I wouldn't say 5/2 seconds and stuff. This is fair. This is fine. So 0.5 seconds into it. Now, part B does not ask you what is its maximum height, but they ask a variation of it. They say, can the horse clear a fence that is 3.5 feet tall? If so, by how much? We want to figure out its maximum height to figure out, could it clear it? If they say if so, by how much? If it's 4 feet, I don't know the answer. If it's 4 feet, that's half a foot above, right? So subtract 3.5 from it. If it can't clear it, we'll say how much did it fail to clear it by? How much did it, half a foot more, and it wouldn't break its leg. So let's hope this poor horse clears its this fence. How do we find that out? Let's do f of 0.5. Okay, I'm going to plug in the 1/2. F of 1/2 equals negative 16 times 1/2 squared plus 16 times 1/2. Negative 16 times 1/2 squared is 1/4 plus half of 16 is 8. That's negative 4 plus 8, which is 4. Hey, it was 4 feet. So 4 feet. So that's not the answer, but that's the thing. Can it clear a fence that's 3.5 feet tall? Yes. By 0.5 feet. How do I know it's 0.5 feet? Because I did 4 minus 3.5. The distance between those. So boom. By half a foot. Now, it can clear it if it hits the fence at its maximum height. That's the point, right? Not too prematurely or anything like that. Part C, how long is the horse in the air? Okay, so this part here, I'm not going to say we're going to solve graphically, but the concept of the graph is important because what you want to know about this, I suppose this part's important, but notice that this is in essence at plus 0. Negative 16t squared plus 16t plus 0. 0 is the y-intercept. The horse leaps off the ground at time 0. And then half a second into its jump, it reaches its maximum height of 4 feet, no less, of 4 feet. But that's the maximum. Parabolas are symmetrical. Remember, this is an axis of symmetry right here. On the other side of this, 1 second later, the horse is going to hit the ground. Now remember, the horse isn't necessarily launching this far. This is time. But they're asking when. How long is the horse in the air? We're also asking when will the horse hit the ground? It leaps at time 0. It lands at time 1. That's 1 second. So the concept of the graph helps us understand that this is the halfway point, half of a second into there. And a full second later, it does it. So what's the question? How long is the horse in the air? The horse is in the air for 1 second. The horse is in the air for 1 second. Because of that symmetry. So that's how I'm using that part. 1 second. Now, algebraically, there's a way to do that. We can factor and solve using the zero product property, but I want to use the concept of graphs as we're talking about them, especially since we already have the numbers. Okay, that's 28. Let's move on to 29, modeling with mathematics. The cable between, so we saw a question like this in an example before. The cable between two towers of a suspension bridge can be modeled by the function shown where x and y are measured in feet. So you can kind of see they, in essence, have the y-intercept at one of the towers and then another tower sticking out here. The cable is at a road level midway between the towers. There's the cable. There's the function for the cable. Let's go ahead and write that down and figure out what questions they have for us. Y equals 1 over 400 x squared minus x plus 150. Okay, part A. How far from each tower shown is the lowest point from the cable? So how far this way, how far that way? It's more so how far this way, because from the y-axis, how far out do we reach the midpoint, excuse me, the vertex, I should say, of this parabola? That's what we're looking for. So let's go ahead and find the x value of the vertex. So for the vertex, the x value is negative b, that's negative 1, over 2 times 1 over 400. Whew. That's also 2 over 400 or 1 over 200. So 1 over 200, no calculator, that's 1 times 200, that's 200 feet. So 200 feet later, we got it. That's part A. Part B, how high is the road above the water? So they said that the cable is at road level. So the bottom of the cable, the vertex, the y value of the vertex, will represent also road level. So we got to find the y value of the vertex. Let's do f of 200. And I use function notation for that. That's okay. 1 over 400 times 200 squared minus 200 plus 150. Now I know 200 squared, but I'll make sure I can divide this part. That's 40,000 divided by 400. So take those out. So 100 minus 200 is minus 50. So 100 minus 50 is 50. 50 feet. 50 feet is the road level. Part C, describe the domain and range of the function shown. Keep in mind, guys, the parabola only represents this portion between the two towers. So we're trying to figure out, basically, this part. There's no arrows. This doesn't go on forever. This is it. This is it. So domain is limited this time. It is not all real numbers. The domain starts at 0, and it goes on x. Oh, let me put feet here as well. This is contextual. So from 0 feet, from x, all the way, you know what, I'm going to put it at the end. 0, x, all the way. Remember, this is 200, which is half the distance, so this is 400. It goes from 0 to 400 feet. There's the domain. It touches everything there. The range, definitely never all real numbers. The lowest point is 50 feet. The highest point is based on the y-intercept. Now, the y-intercept, where's our equation? 150. The lowest point is 50 feet. The highest point is 150 feet. So, from 50 feet, to use y, to 150 feet is the range. Remember, the y-intercept is also the tallest point there. There's domain and range, number 29. That's a good problem. It's a really good problem. Good application. Number 30. Find the axis of symmetry of the graph of the equation y equals ax squared plus bx plus c. Well, it's negative b over 2a. When b equals 0. Can you find the axis of symmetry when a equals 0? Explain. Well, I mean, we did this all the last two sections. For y equals ax squared plus bx plus c. If b equals 0, keep this in mind, the equation is going to look like y equals ax squared plus c. So this was section 3.2. That being said, when b equals 0, we're going to have a vertex x value, axis of symmetry is how we want to say it. We have an axis of symmetry of x equals negative 0 over 2a. Negative 0 is 0, and 0 divided by any non-zero number, because a is not 0 here, is 0. The axis of symmetry is x equals 0. Can you find the axis of symmetry when a equals 0? Explain. I'm going to type this. I'm going to say it as well. No. You can't find the axis of symmetry when a equals 0. Now, they are asking, explain in the sense of what happens when you calculate it. What happens is you end up dividing by 0. And division by 0 is undefined. However, there's more to it than that. If a equals 0, guys, what kind of equation are we looking at? I don't care if b is 0 or not, so let's say that b isn't 0. If a equals 0, you're looking at an equation that says y equals bx plus c. Well, that's not a quadratic equation. That's a linear equation. So that's really the bigger problem. It's no longer quadratic. This doesn't have an axis of symmetry. Linear equations aren't symmetric. Quadratic ones aren't. It's no longer a parabola. If a equals 0, then it's no longer a quadratic equation. It is now a linear equation. Which, by the way, which, by the way, doesn't have symmetry unless b is also 0, but it's still, no, we're good. Okay, that's number 30. All right, number 31. Attending to precision. Ooh, I might have to use a calculator. Let's see. The vertex of a parabola is 3, negative 1. Okay? Vertex is 3, negative 1. 1 point on the parabola is 6, 8. Find another point on the parabola. Justify your answer. Okay. 3, negative 1. I'm going to rough this one out, but 3, negative 1 is right there. Now, there's a point that's also 4, 5, 6, whatever, 8, right? 6 comma 8. The parabola, the vertex has an axis of symmetry. So this point is 3 away from here at 8. This is a 6 comma 8. That means there's another point that's 3 away on this side, and it's actually right there. It's at 0 comma 8. And that's the precision. So the justification is kind of through the graph, through the axis of symmetry in what it is. So here we go. Find another point on the parabola. Another point on the parabola is 0 comma 8. This is because parabolas are symmetrical. I'm sorry about my typing. I'm actually a great typer. Okay. Parabolas are symmetrical. Let's focus. And the axis of symmetry is on x equals 3. 6 comma 8 is an x value 3 away. You don't have to type all this. 3 away from the axis of symmetry. And so is 0 comma 8, which would have a point at the same height. I'm describing to you in typing form so you can find a way to paraphrase it. Go type this into ChatGPT and say, paraphrase this for me. Actually, ask ChatGPT this question. They'll tell you what to do. All right. Number 32. Don't actually do that. Number 32. Making an argument. Your friend claims that it is possible to draw a parabola through any 2 points with different x coordinates. Is your friend correct? Explain. Okay, let's see. Possible to draw a parabola through any 2 points with different x coordinates. Now, I feel like they're missing a word. Are they, when they say a parabola, I feel like they mean a unique parabola. A unique one. Like, it's possible, guys, it's possible to draw a parabola through any 2 points, period. No matter, with different x coordinates. I thought they said with different y coordinates. Okay. Maybe they don't mean unique. Okay, I'm going to assume they don't mean unique. Through any 2 points with different x coordinates. Yeah, yes, your friend's correct. If it's a unique parabola, no. You can do multiple different parabolas with 2 x coordinates. So I'll give 2 different answers. If your friend is referring to any parabola, then yes, then yes, your friend is correct. Now, this is because as long as they have different x coordinates, they're split, right? And split in some sort of way, it's still a function. I don't know how to say this in any sort of way. You can make any function, any function, unless I'm misthinking that, any function of any type can be generated through 2 points with different x coordinates. I don't know how else to say that. Now, however, if your friend is referring, because I don't know, if to a unique parabola, then your friend is incorrect. I will dispute that. I will disprove it with an example. Here's a point. Here's a point. Your friend says, here's the one parabola I can make through this. And then I say, here's another parabola you can make through this. Okay? Or I say, here's another parabola you can make through this. Right? It's you can do anything through that. It would take 3 points to make a unique parabola. It would take 3 points to make a unique parabola. With different x values. With different x coordinates. Once I have 3, you're locked to just one kind of parabola you can make. Okay. I don't know which version they're talking about. I think they're talking about the first one, in which case your friend's correct. But if it's the second one, I wanted to be sure. Okay, numbers 33 to 34. Okay, so this one you're kind of required, well, sort of. You can calculate this, well, I can calculate this. Use the minimum or maximum feature of a graphing calculator to approximate the vertex of the graph of the function. Yeah, I'm going to go ahead and let the calculator help me here. I guess your teacher wouldn't give you these ones if it wasn't there. But if you wanted to, you could still kind of say it's the negative b over 2a stuff and just make sure you have some rounding bits. So I'm going to go to my graphing calculator. Let's do that. And I'm going to type in that first equation here. So it was y equals, so it was 0.5x squared. Whoops. Plus square root of 2x minus 3. Okay, now here's how the graph thing works. Here's the graph itself. Now I haven't done this in a long time. The trace? Not trace. Calc. I'm going to hit the minimum. Now for a minimum, you have to select a left and a right bound. Select something to the left of the minimum and the right of the minimum. Now they're going to say guess after that. That's because if there's more than one minimum, if your graph did this a bunch, they just mean put one as close to your value as possible. There's only one minimum here in between, so I'm going to hit enter, and it's going to get this in between. So so what do they want? Approximate the vertex. The exact y value is -4. The approximate x value is -1. I'll do 3 decimal places. 414. -1.414. So I'm going to write that out. That is number 33. So the y value is 0.5x squared plus square root of 2x minus 3. The vertex is about -1.414, comma -4, just like that. So let's go back to that graphing calculator. It hit right there. So graphing calculator to the rescue. There it is. And that's the answer. All right, let's keep doing that 3 more times. Number 34. Now notice I hit minimum on that one here. And I don't know what kind of calculator you have. Mine's a TI-83, if that helps you. At least the emulator. Y equals -6.2x squared plus 4.8x minus 1. Okay, so use the graphing calculator. Here we go. So y equals -6.2 x squared plus 4.8x minus 1. Okay, so the graph, there it is. Let's use calc. I have to hit the second button and then hit trace. This time I want to select maximum because maximum, it hits the highest point here. Left bound, that looks good. A right bound. Now you don't have to drag over with the arrow. You can just press a number on your thing, but I'll do that in between left and right. Guess, yep, we're going to hit the top. Is that 0? Nope. 0.387 for x, and the y is -0.071 if I round it up. So for vertex, it is, I'm going to write it first. 0.387, I can't remember this number. 0.387 and then -0.071. Okay. So that's what I'm getting for that one there. Number 35. Y equals -pi x squared. I kind of want to do this without a calculator. Plus 3x. Nah. Okay. Let's go. I'm like, I want to do that. Mr. Robinson, you've gone 100 minutes on your thing. Can you just keep going? Y equals -pi x squared plus 3x. Okay. Well, it's going to hit 0, but that's not the vertex. Okay. So hit a maximum. So check this out. Left bound, I'm to the left. Now right bound, again, I don't have to drag over with the right arrow. I could hit like a 2 and it'll go like, okay, now that's over there, right? Left of that and right of that. The maximum is 0.477, comma 0.716. Sorry, I wasn't sure if they were going to say tell us whether it was a min or max. No, they just said use the min or max feature. So 0.477 and 0.716. So there's that one. Number 36. This will go a lot faster if I had an actual calculator because I have to click on these instead of actually type on it. But I need you to see them, of course. So number 36, excuse me. Y equals 0.25x squared minus 5 to the 2/3 power x. Remember how that works? Plus 2. That's the cube root of 25 also. I don't know what that is, but I'm just saying that that's how that works. Okay, so let's bring that up. I'm going to do 0.25 x squared minus 5 to the 2/3 power times x plus 2. Okay. Ooh, interesting. Okay. Minimum. Left bound, yeah, over there. Right bound. Okay, what's right of here? Probably about 9 or so. 9's for sure over there. Okay, yeah, guess anywhere in between those two. 5.848 and negative 6.54550. I'm rounding up 3 decimal places. So let me write that first. See if you can understand what I said there. The vertex x value is 5.848. The y value is negative 6 point, instead of 549, people have trouble with this. I round up the 49 to a 50, right? Because the 8 is higher than 5. So 550. That's if I'm doing 3 decimal places, which I am. And so that is that result. There we go. Okay, that is those. Those are that for that is those four. All right, number 37, modeling with mathematics. The opening of one aircraft hangar is a parabolic arch that can be modeled by the equation y equals negative 0.006x squared plus 1.5x, where x and y are measured in feet. The opening of a second aircraft hangar is shown in the graph. So we have a model of one with an equation that we don't see. And then we have the graph of one, which we do see. Okay, so I'm not going to write anything yet. Let's see. Which aircraft hangar is taller? Which aircraft hangar is wider? Okay, to answer the taller one, we have to find the y value of the vertex of both of these. For this first one right here, this one is about, it's about up there. It's about 100 feet, right? A little bit more than 100 feet, I think. About 100 feet. So if we get a y value that's like 110 or something, I think this is less than it. But if it says 100 or less than 100, then I think this is more. So hopefully it's considerable enough that we know. So for this other one, y equals negative 0.006x squared plus 1.5x, part A, let's go ahead and find the x value of the vertex to then find the y. So the x value is negative b over 2a. I'll let the calculator do the work here, so you don't have to see it. I'm just going to type it out. 1.5, this will turn positive, but 1.5 divided by 2 times 0.006. So, 125. Good. Nice clean number. So 125. And that is good. So, by the way, that's 125 feet as we're talking about some things later here, right? This is all going to be about distances later on part B. But part A, we need to find now basically f of 125, which is going to be negative 0.006 times 125 squared plus 1.5 times 125. I have no idea if this is going to be taller or shorter. So let me plug that in. Give me 1 second. Negative 0.006 times 120. You guys try it too at home, right? Squared plus 1.5 times 1. Okay, I'm getting 93.75. 93.75. And that's exact. 93.75 feet. So, the other one, so this is like hangar 2, right? Hangar 1 is about 100 feet. So, hangar 1 is taller. Okay. Part B. Which one is wider? Hangar A goes to about, oh, this is close. But, oh, you know what's going to very much help? You see these doors? You see how the door line, I assume, is in the middle. Now, if you look at the scaling here, these go by 25s. It's 25, 50, 75, 100. 125 is that blue line. You see the blue line? Which is right of the door line. The door line's the middle of the hangar, so that door line must be left. And that's how I kind of drew the thing as well. It's just left of that 125. So this is important because hangar A vertex is something, let's say it's 124 comma 90, comma 100. Let's see. Oh my goodness, why does that happen? It's about 124 feet, comma, about 100 feet, probably 101 feet or so. Now that 124 though is less than 125. Remember the other one was 125 feet. The halfway point. Oh, here's another way. Here's another way you can tell. This thing hits short of 250 as well, right? 225, 250. So I don't know how much it actually is, but the halfway point is also indicative of what the full distance is, right? If you're shorter halfway, then you're shorter in full as well. So that's how it's going to work. They don't ask me to explain. I'm telling you how that thing's going to work. So I'm just going to go ahead and straight up say that hangar 2 is 250 feet wide because you double up from its vertex to the other point. We talked about that for the horse leap. Hangar 2 is 250 feet, which is wider than hangar 1. And you know what? I'm saying these numbers backwards. They said the opening of one aircraft hangar is a parabolic arc modeled by the equation. The equation 1 is hangar 1. So let's change these. Hangar 1, hangar 2. Hangar 2 is taller. And now hangar 1 is the one from the equation. Okay. Hangar 2 here. This was hangar 1. Okay. There's 37. Number 38. An office supply store sells about 80 graphing. Hey, that's the graphing calculator I'm using. Sells about 80 graphing calculators per month for $120 each. Yep, they're still that expensive. For each $6 decrease in price, the store expects to sell 8 more calculators. I hope I don't have to make the model. The revenue from calculator sales, good, is given by the function R of n equals unit price times units sold, or R of n equals 120 minus 6n times 80 plus 8n, where n is the number of $6 price decreases. How much should the store charge to maximize monthly revenue? Okay. R of n is the revenue model. So we're looking at number 38. Okay, we have R of n equals 120 minus 6n times 80 plus 8n. Okay, before we do anything on this problem, let's understand it. An office sells 80 graphing calculators per month for $120 each. For each $6 decrease, the store expects to sell 8 more calculators. So there's something that says, hey, we lower the price, we're going to make more sales. That doesn't necessarily mean you make more money, though, right? Because you lower the price. So there is this equilibrium. You have to figure out at what price point do we set to get that right amount of sales to make the most amount of money. That's what this model is doing for us. And it makes total sense because this model, and actually I guess I could have made this model really easily. This model is saying, hey, Every time you decrease the price, for every $6 price decrease we do from 120, right, that's going to be the price point. If I decreased it 3 times, then it's 120 minus 18 and blah, blah, blah. This is how many more customers will pay for it. 80 at the baseline for this, and then another 8 customers in addition to that'll buy it. If you take the price point per customer, per sale, times the number of sales, then you get how much money you make, revenue-wise. Not profit, but how much money you make revenue-wise. So it's a product. So we're making sense of the problem. To make further sense of the problem, the first question, how much should the store charge to maximize monthly revenue? We're trying to figure out what the price point should be to then get a maximum. Sounds like vertex related things. So to get a vertex, we're going to need to use negative b over 2a. To use negative b over 2a, we need an equation in standard form. To get that, we have to multiply. We have to FOIL. So, multiplying all these things out, first, outside, inside, last, that kind of thing. 120 times 80 is 9,600. Plus 8n is 960n. Minus that is minus 480n. And then minus 48n squared. Now, I want this in standard form. So r of n equals, so I have negative 48n squared. Looks like plus 480n plus 9,600. So here's our model in a standard form set. If I did the math right, that'd be the standard form set of the model. So part A, let's find the price point to maximize revenue. Solving for n doesn't give us the price point. Solving for n gives us the number of $6 price decreases, and then we use those $6 price decreases to find the price point. But we only need the n portion of it. They didn't ask what the maximum revenue would be yet. So the vertex n value is going to be negative b over 2a. Linear coefficient, quadratic coefficient. That's negative 480 divided by negative 96. I mean, it's a great problem. It's ambitious. There's a lot to it. I don't know what that divides. Let's see, 5. So 5. I hope it's not a decimal. So 5. This is 5 price decreases. Let's see how they say it. N is the number of price decreases. 5 price decreases. Now, they asked not how many price decreases, but how much should they charge. This number of price decreases will maximize revenue. So they should sell them that cheap. So 120 minus 6 times 5 is going to be 120 minus 30, which is 90. I think, you know what's funny? Oh, excuse me. I was going to say $90. Oh, yeah, $90. This isn't revenue. This is a $90 price tag. I'm going to say that. That's how much they should be charging. $90. I wonder if this is the book's way of saying, Texas Instruments, do something about this. You'll make more money. We'll get more say. You know what I mean? But they kind of control that corner of the market, really, above Casio. Casio might be stepping up these days. Part B. Using a different revenue model, the store expects to sell 5 more calculators for each $4 decrease in price. Which revenue model results in a greater maximum monthly revenue? Explain. Okay, so now they are expecting you to now create a new model based on this. There's a lot to do in this problem. We're going to create a new model based on this. We're going to expand that out, and we need to find the Y value of each vertex. Each of them. Still this one. I only got the 90 still. We need to find the Y value of each vertex and compare them. So there's a lot to do. So the last time they said using a different model, store expects to sell 5 more calculators for each $4 decrease. So instead of 120 minus 6n, it'll be 120 minus 4n. So 120 minus 4n. Let's name this a different thing, by the way. Different model. Let's call it Q of n. Q of n is 120 minus 4n times, they expect to sell 5 more calculators instead of 8. So 80 as a baseline, that's still the 120 and 8, plus 5n. Okay, so let's do some of the vertex stuff here, but first we have to FOIL this guy out. Okay. And we're going to get Q of N. So that's still 9,600 plus 600N. That is not 600. Plus 600N minus 320N minus 20N squared, which is negative 20N squared plus 280N plus 9,600. Okay, so this N value of the vertex, negative B over 2A, which is negative 280 over negative 40, which is 7. 7 price decreases. So 120 minus 4 times 7 is 120 minus 28, which is 102. They're setting a $100 price tag. That does not mean they will make more money, because you only get, because like less customers or whatever, less sales. So we have to compare the $102 price tag to the $90 price tag for their own respective models. So R of 90, the question is, what is R of 90 and what is Q of 102? Now, you do not have to use the quadratic model to get it. In fact, I'm kind of more partial to use the factored form, because we can tell a better story with these ones as far as what the price tag was. I'm sorry, we don't use R of 90 and Q of 102. We use R of, you know what? I didn't need the 102 technically, but you know what? I am going to use the 102. I am going to use it. We need to use R of, not 90, R of 5 price decreases and Q of 7. There it is. This can tell a better story to us. It can tell us what the price tag is and how many sales they were and multiply it. Better than using that model. Honestly, it is. You have a factored form. So 120 minus 6N, we already know that that's 90, but 120 minus 6 times 5 times, we never found out how many sales, 80 plus 8 times 5, which is 90, right? We already figured that one out. And 8 times 5 is 40. 80 plus 40 is 120. 90 times 120. I can definitely do this without a calculator. 10800. That's how many revenue bucks we're going to get for the first model. The second model, let's see how the second model pans out. We're going to do 120 minus 4 times 7. We found out that was 102, which we didn't need at the time. But and then 80 plus 5 times 7. So this is going to be 102. I might need a calculator this time. 102 times 115. I can do that in my head. I'll tell you what, this answer's more. It's 730. I'm gonna do that in the calculator now. I think it's 11,730. Let's try that. 115 times 102. 11730. Okay. All right. The new model is better. So how do they say it? Which revenue model? The new revenue model. How do you spell revenue? The new revenue model generates, I was thinking NEW, generates more revenue. The new model generates more revenue based on maximizing it. Maximizes more revenue, I should say. Not generates, maximizes. Because it depends on how you do it within the month or whatever they say. Okay, maybe their statement isn't as underserved as before. Maybe they're like, hey, you know what? Never mind about the $90 price point, Texas Instruments. Do the $102 price tag. You'll make less sales, but you'll make more money. All right? You'll do that. All right, let's do that. Yeah, man, it's hard to, it's when they corner the market, it's hard to find a good sale on those. It's always the same each time. We still have a ways to go, guys. I'm at the 2 hour mark. We still have a little ways to go. In exercises 39 and 40, find the value of x that maximizes the area of the figure and find the maximum area. So we definitely have to work a little bit in these models here on out. There's a lot to do on these guys. I'm going to copy and paste this in. You might have to draw it out if you're working on it. So let's see. Number 39. Which way do I want to go about this? X, 1.5, x, 6. There's overlap. I could subtract. It's 1.5x. Oh. I'll do this. Okay. What I'm trying to do... Oh, you know what I could do? I'm sorry. You know what? Never mind. I'm going to do something else. There's more than one way to do this. Okay. Find the value of x that maximizes the area of the figure and find the maximum area. So basically, we want to express this area as a polynomial. What I'm trying to do is find a way to express that. So there are a couple ways we can do this. We can cut this off here. Actually, cutting off there would be pretty good too. I might do that. Let me show you two different ways. Or three. I don't know how much I want to pain myself. We can cut it off here, or we can cut it off here, or we can find the area of the big guy and subtract the area of this guy. That's what I was thinking of last. So let's start with this one. If I did this, option number one, we would, now this 1.5x is no longer 1.5x, right? 1.5x is here, the whole thing, but this little guy right there is just x, and so this is 1.5x minus x, which is 0.5x, right? So this total for option one, we could take, and this height, and that height, this height is 6 minus x right there. So for option one, we have the area of this one being x times 6 minus x. And then this one is 0.5x, or 6 times 0.5x. And then we go ahead and add those together. So x times 6 minus x plus 6 times 0.5x, like that, which is 6x minus x squared plus 3x. So negative x squared plus 9x. So there's option one to get that value. Option two. And I have to erase this, but option two. Cut it off right there. This is still 6 minus x. And this is x right here now. X right there. And this is still 0.5x. So option two. Option three is my favorite, by the way. Now, that's why I said, I'm going to do option three. Option two is we now have x times 0.5x here. And here we have, this is probably my least favorite one, 1.5x times 6 minus x. Ugh. So option two, it's 1.5x times 6 minus x plus x times 0.5x. So this is going to be 1.5 times 6 is 9. So this is 9x minus 1.5x squared. And this is plus 0.5x squared. Negative 1.5 plus 0.5 is negative 1. So we get negative x squared plus 9x. Option three, to get the same thing, the one that I kind of like the most now that I kind of saw it. Option three is you take the area of the entire, what would have been an entire thing, this entire guy here, which is 6, I shouldn't really point at the white, but just the whole thing, it's 6 times 1.5x, and then this guy's x squared. So we're going to do 6 times 1.5x minus x squared, just like that, because that was x times x right here. 6 times 1.5 is 9x, so you get 9x minus x squared, or negative x squared plus 9x. That's my favorite one. Okay, a lot of work, a lot of different things to show three different options so you can understand how we're getting the area in one way or the other. Find the value of x that maximizes the area, then find the maximum area. So no matter what, we are working off this model. So the vertex, it's all about vertex. I don't have to graph it. It's just all about the vertex. The x value is going to be negative b over 2a, which is negative 9 over negative 2, which is 9 halves. So that's the x value that'll maximize the area. The maximum area, and by the way, this is in inches. So 9 halves inches is the one for x. The maximum area, that was part A. Part B, and by the way, I'm not going to do 3 different options for another problem. That was just to kind of talk about what we're doing. Maximum area, let's do some f of 9 halves. I know that I didn't write it as that, but f of 9 halves is going to be negative 9 halves squared plus 9 times 9 halves. Negative 9 halves squared is 81 fourths, and negative 81 fourths plus this is 81 halves. Guess what? That is 81 fourths square inches. Now, I don't know if this counts as a word problem or not. That's an exact answer, but that's also 20.25 square inches. So if that helps you out, you can use one or the other. But 81 fourths sounds good to me, and that's the area. All right, that's 39. Let's look at number 40. We have a trapezoid. And you know what? I think it was the last video. It's now that I'm looking at this, I think it was the last video that I did that calculus kind of thing at the very end. It was like the last or second to last problem. And there was they said approximate the area of the parabola. And I said, I'm just going to use a triangle. It's going to way underestimate it. But I could have used trapezoids. And I said, I don't want to do it. I told myself, I don't want to do it because I don't know whether we do trapezoids or not in whether you guys know about trapezoids or not. But it looks like we might have to know about trapezoids here. So maybe I should have done it then. It would have given a much closer approximation, which is what we would have done. There's something called a trapezoidal rule in calculus to approximate things for curves. So I totally would have done it. Anyway, if you didn't watch that thing, you have no idea what I'm talking about. But I didn't use trapezoids anyway, and now we're going to. So the area of a trapezoid to begin with, by the way, I'm not saying you shouldn't know it. We didn't talk about it before, is you average your bases and you multiply by your height. So here's a base, here's a base. So we're going to take 1/2 of 12 minus 4x plus 12, right? This plus that times height, x plus 2. So half of 12 plus 12 is 24. I was trying to think whether I should write it first or second. 24 minus 4x times x plus 2. I don't know whether I should write it first or second. Let's take half of that. That's 12 minus 2x times x plus 2. And now let's distribute this out. So this is going to be 12x plus 24 minus 2x squared minus 4x. And combined in standard form is negative 2x squared. 12x minus 4x is 8x, and then plus 24. Whoops, plus 24. Now, what I should have mentioned on the previous problem, and I'm going to mention here, is don't automatically assume to just find the vertex to maximize something. You have to make sure you understand that this is something that you maximize. When a is negative, the graph is upside down. When the graph is upside down, you hit a maximum. But what if a was positive? The vertex is not a maximum anymore. The maximum will occur based off a domain restriction here or here, and knowing the graph will be more important. So just make sure you understand that maximum's at a vertex when a is negative. In this case, a is negative, so it works out. So for part A, let's find the x value that'll maximize this area here. So the x value of the vertex, which is where it works, is negative b over 2a, which is negative 8 over negative 4, which is 2. This is 2 feet. That is part A. Part B, find the maximum area. Now, once again, it's one of those things. You can substitute it into here. Like, it will be 12 minus 8. 4 times 2 is 12 minus 8 is 4. 4 plus 12 is 16. Average that is 8. Times 4 is 32. We should get 32, but I'll plug it into the formula. So I probably could have done it that first time as well. Oh no, the first one had ugly numbers, didn't it? Never mind. This one's good for it though. What I assume 32? We'll see if that's what it is. Did I say 32? I can't remember anymore. Okay. 2 squared is 4 times negative 2 is negative 8 plus 16 is 8 plus 24, yeah, 32. So 32 square feet. That's the maximum area we can get if we have 2 for x. Any other number for x wouldn't maximize it, or it might not be a trapezoid. All depending on what you're doing. Okay, number 41. Compare the graph of this and with the graph of this. Okay. Oh, yeah, duh. We do some graphs. I was thinking about other things. I'm like, all right. All right, number 41. We have g of x equals x squared plus 4x plus 1, and h of x equals x squared minus 4x plus 1. Don't assume they're anything alike each other. I mean, they'll both go up, like stretch factor is 1, but don't assume that they're just left and right of each other. I make no assumption of that whatsoever. So for g of x, it's all about vertex stuff right now, right? The vertex x value is negative b over 2a, negative 4 over 2, which is negative 2. Now, this guy's vertex value, therefore, would be positive 2, right? It's just that negative b is opposite of negative 4, things like that. So now, we also plug them into these functions. So g of negative 2, is negative 2 squared plus 4 times negative 2 plus 1, which is 4 minus 8, negative 4, plus 1 is negative 3. So the vertex of this guy is going to be negative 2, negative 3. This one, on the other hand, is h of positive 2, which will be 2 squared minus 4 times 2 plus 1. Oh, they're both plus 1. Which is 4 minus 8 is negative 4, plus 1 is negative 3. Oh, they are right next to each other. Oh, well, go figure. The vertex is at, I guess that makes sense, same y-intercept. I thought one was a minus 1, one is a plus 1. The vertex is at 2, negative 3. Okay, fine. So, as far as comparisons go, check this out. Same stretch factor. They both face up, so they share the same vertical stretch factor, face upward, and have the same y-intercept. Like, they literally cross at the same thing. However, they are 4 apart from each other. 4 units apart from each other in the x direction. See vertexes above. But anyway, make no assumption in those cases that those things happen. Some other things really may have to vary with that, especially because you plugged in different x's and they have different equations. So there's the bit. But looks like that one works out the way that it does. All right, that was number 41. Let's go to number 42. All right, how do you see it? During an archery competition, an archer shoots an arrow. Hi, I'm Archer. My impressions aren't good today. All right, during an archery competition, an archer shoots an arrow, just like Archer. The arrow follows the Do I sound like Archer at all? I'm not quite sure. The arrow follows the parabolic path shown where x and y are measured in meters. What is the initial height of the arrow? The initial height is where it's shot off. It's right there. Y-intercept, baby. It's 1.5. So part A, I'm trying to say, what? Do I use y? Y equals 1.5 meters. Okay. Initial height. B. Estimate the maximum height of the arrow. Basically looking at the graph. We don't really have an equation. It looks like around, is it at 20? It looks like a little left of 20, right? But they said the height, not the actual value. So 1.6 about? Y is about 1.6 meters? That's my guess. Part C, how far does the arrow travel? It's about 90 meters. I mean, there's not much to this. It's just looking at the graph. X is about 90 meters. I don't even think we have to say Y and X on these things here, but it's looking good. It's looking good. Yeah, it looks like that's it. Okay, 43. The graph of a quadratic function passes through 3 points. See, there's only one. See, this is where I wonder for that your friend thing. If they talked about a unique one, they just said a quadratic function. This is a unique one here, and they didn't say it, but it is. Passes through these 3 points. Does the graph open up or down? Explain your reasoning. Okay, let's look at these 3 points. Let's look at 3, 2, 4, 7, and 9, 2. Now, I hate explaining these sometimes, like in typing words. Like I can show you visually what it's going to look like, but I'm not really good at explanation going like, because look at it, right? So let's see if we can have a good way of explaining these. These are on the first quadrant, so I'm going to move it like this more so. So in this first quadrant, I have 3, 2. I'm just roughing these. 3, 2, 9. Oh, this will be an easy explanation. 9, 2, and 4, 7. Does this graph open up or down? Well, this one would have to hit these 2 points here, top out somewhere, and then come back down to hit that other one, right? In order to be a function. In order to be a function. They say quadratic function, and that's what we're talking about. So this graph opens down. This is because the point between 2 other points of the same height is above those 2 points. And to be a function, hold on, not period, I'm just going to shrink it. And to be a function, it must pass the vertical line test. Here's my point on that last part. You could simulate and make up other graphs. You're like, no, check out this parabola. Number one, there are things called sideways facing parabolas, which I guess this also wouldn't work because I have 2 with the same y value for a single x. 2 with the same y values for different x's. Number 2, we could probably make some version that's like, oh, look, the graph, I guess that would still be upside down. I could make one that's right side up if it goes here and then comes back and does that. But no, you can't have one that goes that way, right? That's not a function. So it needs to be a function. It needs to kind of come up here. And by the way, this isn't the vertex. It's not like it does this, but it does probably go up there, hits something up there, and comes back down. Anyway, that's just a support bit for 43. Let's go to 44. For a quadratic function, what does f equals negative b over 2a represent? Explain your reasoning. Well, here's what we learned. We learned that negative b over 2a is the x value of your vertex. And when you substitute the x value into your equation for y, you find the y value of the vertex. So f of negative b over 2a, I'm going to write this, represents the y value of the vertex. Did they say explain? I'll type that if so. Represents the, yeah, explain your reasoning. Represents the y value of the vertex. This is because negative b over 2a is the x value of the vertex, and f of negative b over 2a means to substitute your x value and find your y value. Therefore, ergo, da 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 da. All right? That seems to make sense, and that's what we're getting there. And if I substitute negative b over 2a into ax squared plus bx plus c, you'll see how that ax squared plus bx part, when they add together, becomes the opposite of the other thing. I'm not going to do that unless they need me to. All right, problem solving. Write a function of the form y equals ax squared plus bx, whose graph contains the points 1, 6, and 3, 6. Okay. So 45. So we need to write y equals ax squared plus bx containing 1, 6, and 3, 6. Here's the thing about ax squared plus bx. The c is 0. The y-intercept is 0. So that means that we are hitting 0, 0 for sure. Now we're also hitting 1, 6. And we're also hitting 3, 6. Like that. Okay? So I'm trying to make sure that I don't overspeak on something that's like, well, hold on, that's a little highfalutin. You haven't learned that yet. We do have to find the vertex, but the x value of the vertex is going to be, because these are the same height, this is part of the symmetry. So right in the middle is this 2. The axis of symmetry is at x equals 2. The question is, do we have enough information to produce A, given this information without not knowing what to do, like without you not knowing what to do on it? So that's what I want to sit on that for just a second and think about how would you specifically know what the A value is with this information. Great. Yeah. Okay. Yeah. We can just do a system of equations. It's assumed, I guess, at this point in integrated math 2, you've used a system of equations for this. I don't know how much the 0, 0 mattered. I'm trying to think if the 0, 0 matters. But 1, 6, and 3, 6 do matter in this case here. Yeah, it should totally matter, right? Because we gotta hit y-intercept of 0, right? That's what makes. I guess the fact that it doesn't have a plus c means it doesn't. You don't need to know it hits 0, 0. We just need to know that we have a c of 0 and we're good. So we're gonna substitute 1 for x and 6 for y in one equation. We'll have an equation that says 6 equals a times 1 squared plus b times 1, or I'll get that better later. And 6 equals a times 3 squared plus b times 3. So this is better rewritten as, I'm going to write this first. 1 squared is 1 times a is a, plus 1 times b is b, equals 6. And this one is 9a plus 3b equals 6. Okay, in a system of linear equations such as this one, we'll solve for a and b. I can multiply. I'm not going to talk too much about how... I'm not going to explain. I'm not going to teach system of equations right now. I'm going to multiply everything here by -3, and I get -3a minus 3b equals -18. And that gives me 6a equals -12. So a equals -2. I'm trying to make sure that that works. Yeah, that does work for that. A is -2. So if -2, I'm going to plug it into this top equation. -2 plus b equals 6. Add 2 to both sides. B equals 8. So your equation will be y equals -2x squared plus 8x. And then the plus c is 0. So, yeah, the vertex is right in the middle. I guess that didn't necessarily matter either for us, but we can confirm. You get -b over 2a here. You're going to get an x value of 2, all that kind of stuff. And that's the form. Systems of equations. Haven't seen those in a long time, have you? All right, let's go to the last 4 problems. Number 46. Critical thinking. Parabolas A and B contain the points shown. Identify characteristics of each parabola if possible. Explain your reasoning. I don't think they're asking us to compare them. So I think it's almost like 2 different questions. So part A for parabola A, that's tough. Notice how they do say if possible. Remember, okay, time out. Remember the whole friend thing? Your friend said whatever. You cannot make one unique parabola with these 2 x values. So for part A, for parabola A, I'm just going to say not possible. I've already shown you on a previous problem. I forget the number. It's the your friend argument, making an argument. Not possible. 2 points are not enough to represent one unique parabola. It does take 3 points. I even said that much. I said 3 points is enough to make a unique parabola. This just is enough. You can make any parabola in the world, not anyone. They have to pass through these 2 points. But I can make upside down parabolas, right side up parabolas. They can be wide, they can be narrow, they can be a bunch of different things. We don't even know the y-intercept on that one. So that's a not possible to do specific characteristics. I don't even know if it faces up or down. Part B, we're going to be able to know enough about it. It's 3 points. They're different x values. We can make a function out of it. So let's look at this one. Let me just say 2, 3, and 6, 4. Okay, so this next one is 1, 4, 3, -4, 5, 4. Okay. Same thing. This is kind of first, also fourth quadrant. But we have like 1, 2, 3, 4, 5, and like 1, 2, 3, 4, 1, 2, 3, 4. Okay, 1, 4, 3, -4, 5, 4. There's a lot of things we can get out of this. I could make a full equation if I wanted to. They just said identify characteristics though. For one, this is the vertex. These 2 points are the same height, and they are the same distance away from this value, right? So this is the vertex. So vertex is 3, negative 4. Number 2, the graph faces upward. This thing is doing that right there. It's going to have to hit there. Graph faces up. If we worked hard enough, we could come up with a whole equation. I could tell you right now it's going to be some 2x squared, blah, blah, blah. They just identify characteristics. I'm trying to think of what else I'd want to say characteristically. Range. How about range? Domain's all real numbers, but range is y is greater than or equal to negative 4. I mean, in a minimum, whoops, at negative 4, axis of symmetry, x equals 3. I mean, I'm trying to say some of those things. If you made an equation, you would have to do a system of 3 equations to get that. I don't think they're asking us to come up with the equation. They said characteristics. So I'm going to kind of cut it off there. But it's going to be some 2x squared mumbo jumbo. Okay, that's number 46. Let's go to number 47. Modeling with mathematics. At a basketball game, an air cannon launches t-shirts into the crowd. The function y equals negative 1/8 x squared plus 4x represents the path of a t-shirt. The function 3y equals 2x minus 14 represents the height of the bleachers. In both functions, y represents vertical height in feet, and x represents horizontal distance in feet. At what height does the t-shirt land in the bleachers? Okay, so in this kind of problem, I don't know if I want to do this graphically. This is one I kind of want to do as an equation if it's valid. I want to see how the equation part works with regard to what we can do. If it's non-factorable, I'm going to go to the graphing calculator and find where they intersect, because you guys haven't done chapter 4 on solving irrational equations. I don't want to speak too far on that if it's factorable. Y equals negative 1/8 x squared plus 4x and 3y equals 2x minus 14. Okay, first things first. When it comes to what they're talking about, this is all about this kind of thing. Now, I don't know what this thing specifically looks like yet. I'm going to imagine that the stands are some sort of like, yay, we're the stands, right? It's like this is facing on the side. Here are people, and they're overlooking the game, right? Now, there's an air cannon that's doing this right there, and it's hitting the crowd like that. When does it hit the stands? We're trying to figure out when this parabola hits this line. That's the kind of thing we're looking for. Boom. At what height does it land in the bleachers? It's not a vertex question, unless it hits at the maximum height. But that's not an assumption. Anyway, what we want to do is we want to find the x value where they intersect first, and then substitute that x to find the y. To find the x value, what we have to do is manipulate this equation here, or this one, both, so that we can set y's equal to each other. So I have to divide this equation by 3 right here. And I'm going to get y equals 2/3 x minus 14/3. And I want to set these equal to each other. Set equal. Set one y equal to the other y. For what value of x do we get the same y out? Now that's just the beginning of this problem. We get negative 1/8 x squared plus 4x equals 2/3 x minus 14/3. The next aspect of the problem is I hate fractions with these, so do you. So we have to multiply by something that's going to clear out the fractions. If I multiply both sides by 8, it'll clear out the fraction on this side. If I multiply both sides by 3, it'll clear out the fraction on this side. If I multiply by the least common multiple of 8 and 3, which is 24, it'll clear out the fraction on both sides. Distributing the 24 into here, 24 over negative 8 is negative 3x squared. 24 times 4 is 96. 24 times 2/3 is 16. And 24 times negative 14/3 is something. Negative 112? Yeah. Negative 112. If I move everything to one side of the equation, getting my x is positive, my x squared positive, I'm going to add this over, subtract that over. I'll have 3x squared minus 80x minus 112 equals 0. Is this factorable? I have no idea. I don't even know factors of 112. Let's see. This takes more tests because the number is a little bit different. 112 is 112 and 1. It is 56 and 2. I hope I multiplied that right before. 56 and 2. It is doesn't divide by 3. It is 4 and 28. It is not 5. 6. I'm sorry that I'm trying to factor this one first. If it's irrational, I have no idea. It is doesn't divide into 6. 7. I don't know, but it does divide into 8. 8 and 14. 9, 10, 11, 12. No. I think that's the extent to what they divide into, right? Right. Yeah. 7. It does divide by 7. 7 and, not 14, 16. 7 and 16. Okay. So those are my options here. Let's test 3x and x, 1 positive, 1 negative. That'd be impressive if this thing works. 3 times 28. Oh. This is factorable. Check this out. 28 and negative 4. You know what 3 times 28 is? 84. 84 minus 4 is 0. So it does factor. So if 3x minus 4 equals 0, then x equals 4/3. If x plus 28 equals 0, then x is negative 28. You can't have negative. It's not you can't have negative distance. It's that the stands, I'm guessing, I still haven't worked out this equation, but my guess, actually, you know what? I do have to look at that. I don't know which way this graph goes. I haven't looked. 2/3 x minus 14/3. Yeah, it does go this way. So negative 28, that's not going to be it. The graph goes, for the stands, the graph goes out that way. So it's going to hit somewhere out there. Only at 4/3 though. So that's not, I'm sorry. This is backwards. Oh, time out. I didn't need 80, negative 80. I didn't need 80, I needed negative 80. So this, let's go the other way. I'm sorry. It is this way. So 3x plus 4 equals 0. X is negative 4/3. That one doesn't work. But here, x minus 28 equals 0. X equals 28. That does work. Okay, cool. At what height does the t-shirt land in the bleachers? Now, I need to substitute 28 into either this equation. I don't want to do it into my quadratic. I'm just going to get 0 back out. I substitute into this equation or this equation. Either or is going to work because it's the same y value out. And then we solve for y from there. So let's do into the linear equation. Let's get y equals 2/3 times 28 minus 14/3. 2/3 times 28 is 56/3 minus 14. Minus 14/3 is 42/3, which is 14. It'll be 14 feet high. That was all without a calculator. I hope I did that correctly. But at what height does the t-shirt land in the bleachers? At 14 feet high. It's going to be that guy. So, kind of tricky. A lot of stuff to go. Whew. The graph barely did much for us, but it did do something for us. Okay. 2 more questions. Number 48. This will be the longest video, I think. I didn't know how long or short this was. I was really hoping it would be shorter with less graphs, but oh boy. These are big questions. One of the 2 classic, what is that? One of the 2 classic problems in calculus is finding the slope of the tangent line to a curve. Yes. An example of a tangent line which touches the parabola at just one point is shown. So it's a way of saying it just nicks and kisses the curve and it goes off. It doesn't crash through, boom, boom, like that. It's a way of finding the slope of the curve at that point, the instantaneous rate of change. Approximate the slope of the tangent line to the graph of y equals x squared at the point 1, 1. Explain your reasoning. So this is an example. This is not the one we refer to. But if you notice here, this slope would be approximately up 1 over 1 like that. That slope would have been 1. What they're asking you to do is to take, and you want to scale this one. So I'm going to grab graph axes here. Okay. I'm going to take a look at y equals x squared. So 1, 1, 2, 4, 3, 9, etc. Now, I already know this answer. I know it through calculus, but we'll try it. It's tough because when I know the answer, my approximation is like, yeah, I'm going to make it look perfect. All right. What I really want to do, though, I really do need to make this curve look pretty good. Otherwise, it's moot in terms of what we're doing. I just made it terrible. Really, I need it good at 1, 1. Doesn't matter what it is the rest of the way, but okay. This probably does that, right? Okay. At the point 1, 1, they're asking you to approximate what that tangent line would be, what the slope of it would be, okay? So they're asking you to kind of rough out a tangent line to make one that would be just kissing off that thing. And let's make it green. Okay. Make a tangent line that just kind of kisses off that thing and kind of goes off from there. I don't know if what I made is actually looking perfect or not. It actually doesn't look all that perfect anyway, but just kind of, kind of hitting that and coming back off like that. Boom. They're saying approximate. Yeah, that's looking pretty good. As you can tell, I'm trying to get to the answer. That's a good tangent line right there, wouldn't you say? When you say it's a pretty good tangent line, I think it's a pretty good tangent line. Hey guys, what's that slope of that tangent line right there? Looks like it's going a little up 2 over 1. Little up 2 over 1. Looks like that slope is about 2 over 1, which is about 2. Is that pretty good? Pretty good slope right there. Yeah, it's looking pretty good. Yeah. It's just so that the slope of the tangent line there is 2. But it looks like it too, right? That makes sense because that's the curve, it's to scale, and that's what it's supposed to be. So that's what they're asking you to do for that thing, though. I don't know what, I guess we had to graph y equals x squared, but that didn't have much to do with what we're doing right now. X squared plus bx plus c. Okay, last question, problem solving. The owners of a dog shelter want to enclose a rectangular play area on the side of their building. They have k feet of fencing. What is the maximum area of the outside enclosure in terms of k? Hint, find the y-coordinate of the vertex of the graph of the area function. Okay. I'm going to copy and paste that. Let's make sense of the problem. Okay. Here's what's up. The dog shelter building has very little to do with the problem except that it covers a whole side of this thing. That's important. The k feet of fencing, you might think of perimeter. It's not full perimeter because the perimeter only covers these 3 sides. So the k feet of fencing is not 2 lengths plus 2 widths. It's 1 length plus 2 widths. K is 1 length plus 2 widths. Okay? That's important for this. Now, how do I use that? Let's see. Find the y-coordinate of the vertex of the graph of the area function. Oh, yeah. Okay. So the area, the area is length times width, right? Length times width. So when it comes to this here, once again, generally you want to express one thing in terms of the other. K feet of fencing. What's the maximum area? Then outside enclosure in K. I want to express one in terms of the other. Did they say anything else? One enclosure rectangle plane on the side. They have K feet. Okay. To maximize area. Wait. To maximize area or fencing? What is the maximum area? To maximize area, you generally want to square off your thing. No, that's for a perimeter. Oh, shoot. I got to think of how I want to say this now. Length times width, express it in terms of that. Length plus 2w. I don't know why I'm having trouble with this. It's something I can do in calculus all day, but I want to think of it in terms of another one. How do I express one in terms of the other is the question. That's what I want to think about. What is the maximum area? I was like, find the y-coordinate. No, I know that. Okay, this is how. I'm stupid. Oh no, I'm not. That still doesn't do what I want to do. I feel bad that I'm stumped. I want to pause on this for a second. Sorry about this. Give me a second. Let me think about it. Okay. So in rereading the question again, what I'm really looking at is they said in terms of k. So k can be in the answer. I thought they were more solving for k, and I thought we had to express length in terms of width or the other way around. But they said in terms of k. So as long as k is in the k can be in the answer, and you're good. So here's what I'm going to do. I'm going to take this equation. I'm going to just get L by itself. L equals, and I'll write k minus 2w. Now I can go to the area equation and write a model. See, before I was thinking like, wait, that's a third variable, but I can use k in my answer, so that's good. So the area being length times width, it's also k minus 2w times width, like that. Now width, this can distribute, so this is k times w minus 2w squared, or the other way around, negative 2w squared plus kw. Okay, that makes more sense. I was thinking, I can't get a number if I don't know k. My whole goal, okay. K is in the answer. I'm good. All right. What do they want? Right, what is the maximum area of this thing? So to remember, area is your y now. Area is your y. They're asking what width will maximize the area, right? Width is now my variable. So for the vertex, the width is negative b, k, over 2a. Remember, k is the linear coefficient now. So that's negative k over negative 4, which is positive k over 4. Okay, that is the maximum width. If you take a quarter of your fence, so this is cool to talk about, right? If you take a quarter of your fencing for your width, you will maximize your area. Cool. Now, what is that area? So area, remember, k is going to be in the answer. We'll get negative 2 times k over 4 squared plus k times w's k over 4. Remember, this answer is not going to look like anything pretty unless it is. Negative 2 times k squared over 16 plus k squared over 4. Okay, this seems to match up with what we talked about with vertex before. That will be negative 1/8, negative k squared over 8 plus k squared over 4, which equals k squared over 8. So that's the maximum area in terms of k. If we had a number for k, we could plug it in, and then we'd get the area. This is in square feet. Square feet. Okay, that's the answer. Okay, guys. At 2 hours, 42 minutes, 43 minutes or so, that ought to do it for this one. This is near the longest one, if not section 1. Which one was it? 1.6 or 1.3 or something? That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching, and I hope we found what you needed for this material. Next would come the 3.1 to 3.3 quiz review, or whatever it's called, the quiz, whenever I record that, or when you find it there, it should be popping up somewhere here soon. So that'll do it for this one, guys. Thank you so much for watching, and take care. I will see you in the next one.